winter, and it was pity that the name was the same, summer school, but the school actually was in winter. And my name is Vladimir Petrov. I am associate professor at Radiochemistry division of Department of Chemistry of Lomonosov Moscow State University, and I am like a deputy head of this division on radiation safety. Welcome. And I would like to give a floor to Michael Ojavan, our one of the main speakers, and the man who are the big expert in radioactive waste management. Michael, please.
Thank you, Vladimir. I hope you can hear me. So good morning, everyone. I see you on my screen. I hope you see and can hear me as well. So good morning again, everyone. I'm Michael Ojavan, or Mikhail Ojavan, Michael Ojavan, and I'm the only distant lecturer for you. Apologize for that, colleagues, apologize. Last week, I was in a meeting, in a similar meeting online of International Atomic Energy Agency. And the people around the world, they were connected to each other online, like I am now with you, because, you know, the situation is that. At least you are lucky now that you are all in a room and only me, I'm outside. I wish to be with you, and I hope that soon we will get again to this normal situation. So again, I apologize that I will need to give my lecture using distant learning. It has some advantages. It has some advantages because we can connect much more people, many more people to be together and to interact to each other. So I wish you a good 2 weeks work at the International Summer School on Chemistry. It's a regular event which the Moscow State University organizes. It involves many international participants, and it's really a big pleasure to interact with you young people. So the possibility is to give you some material, to learn something from you. So I will continue with my lecture at 2 o'clock. So success. Vladimir, the floor is yours.
Thank you. Thank you, Michael. And now I will give a short presentation about Moscow State University, about education on radiochemistry at our department. Just one moment. So once again, I welcome you at Moscow State University, our biggest university in Russia. And Moscow State University is not only the biggest, but the eldest university in Russia. It was established in 1755. And nowadays, it consists about of 50 departments and different institutes, from social sciences like sociology, I don't know, journalism, even TV education, to fundamental research, to math science, physical science, even Institute of Nuclear Physics, and different biological science like bioengineering, physical chemical aspects of biochemistry, etc. And one of these departments is the Department of Chemistry, and it consists of 17 divisions, again ranging from general chemistry, inorganic chemistry, analytical chemistry, organic, physical chemistry, etc. And one of these divisions is division of radiochemistry, where you now. And this division consists of 6 laboratories and has around 80 employees. The Department of Chemistry in general have more than 1,000 students. We have 6-year education of specialists We also have bachelor degrees and master degrees, but the main, let's say, route of the education is the specialist education in Russian systems. So nowadays it's 6 years of education. So every year we have around 220 to 130 new students. So around 200 of them finish in the education, and we have around 90, 100 PhD students, new PhD students every year. And nowadays we have 4 years of education for PhD students. It doesn't matter in which specialization, in inorganic or radiochemistry or whatever. And we have around 700 scientific staff. It includes professors, associate professors, assistants, and also we have around also 700-800 of scientific staff. So we have around 13 academicians now and 10 corresponding members of Russian Academy of Science. So next, yeah. Division of Radiochemistry, as I said before, consists of 6 laboratories. One of them is a newly organized laboratory of radiopharmaceutical chemistry. It's rather new. It was established only 3-4 years ago. And in our division, we have possibilities to work with hot samples. We have a state license from government to work with radioactive materials, including plutonium, uranium, etc. We have all analytical devices to work with them, and now that is we are a bit proud of it, maybe not a bit, but now we have a vivarium, so we can work with rats and mouses nowadays to test the radiopharmaceuticals in vivo, and not only radiopharmaceuticals, but also we use these animals to test like new implantants for bones and other surgeries. It is in connection with inorganic chemistry division, and other radioanalytical stuff, and let's say conventional chemical stuff and analytical, etc. So as I said, every year we have about 220 students, and again, it was around 4 years ago when radiochemistry become mandatory subjects. It was before also mandatory, but nowadays we have exam on radiochemistry. So previously it was just a passing exam, just a pass or not pass, and nowadays it is like a real exam on radiochemistry, and all the students who are learning chemistry at Department of Chemistry, they have to pass this exam, this subject. And so they have around 36 hours of lectures, so one pair of lectures every week during one semester, and they have seminars and lab exercises, also around one pair of exercises per week. So it is in some 36 hours. And then these students, it is the 3rd year students of the Department of Chemistry. And after the 3rd year, students choose their specialization, and the students who are now on radiochemistry division, they also have special courses on nuclear fuel, chemistry of actinides, biological effects of ionizing radiation, and other special courses on different subjects of radiochemistry. And they also have special lab exercises that's more detailed determination of radionuclides, separation of radionuclides, etc. And now this year, 1 month ago, we have a defense of the first exit or first masters of our new master's program. It is project management in the field of decommissioning of nuclear facilities, including radioactive waste management. So it is a newly formed program where we teach people not only like a basic principles of radiochemistry, but also project management, financial management, and including all the technical details that are related to decommissioning of nuclear facilities. It's not only the nuclear power plants, but also the facilities related to the different stages of nuclear fuel cycle. It can be the plants, the uranium converted to uranium hexafluoride. It's different facilities dealing with enrichment of uranium, etc. So not only nuclear power plant, but all the facilities related to nuclear fuel cycle. And yeah, again, it was organized 2 years ago, and now we had first masters who finished this program. Very small number of students who are going to this program, not more than 10 students. And this first finish was 8 students, and they were successful. We also have different trainings for foreign specialists, foreign students, foreign PhD students, postdocs, etc. They're coming from different countries, from Europe, from America, continents, from Asia. And we also have this nowadays quite a large list of different international schools and conferences. And this school is one of the schools in the series of schools organized together with Rosatom, with Technical Academy of Rosatom. And I hope it's not the last school organized face-to-face. We hope that, really hope that the situation will go better and better. We organize this school also in the framework of the practical agreement with IAEA, and this agreement is related to education programs and to different to participation in different joint research projects of IAEA. Next, yeah, just a few words on what we are doing at Radiochemistry division for science, for scientific topics. First of all, it's a radioecology and environmental radioactivity. I'm personally the head of laboratory of dosimetry and environmental radioactivity. It's a geological disposal of nuclear waste or radioactive waste. It's all the topics related to decontamination of water of lands and purification of waters, groundwater, tap waters, etc. We develop the sorbents and system not only for like liquid waste treatment, but also for cleaning the groundwater contaminated with oil products, etc. It is nuclear medicine, quite a new topic for us, but it's very interesting and very perspective topic. Again, we have a vivarium where we can work with this new radiopharmaceuticals in vivo, and some topics that I'm personally proud of is separation chemistry. It's development of new systems, new extraction systems for separation of actinides, fission products, etc. And one of the system hopefully will be implemented in the real industry quite soon. Again, I hope so. And it's our maybe not the main topic, but one of the most successful topic of our research. It is, of course, material science. We have 2 labs who are working with Miss Bauer spectroscopy. Yeah, their research work also was related to one of the first Mars explorer in early 90s. So they're really good in characterization of iron-containing solids and others. They have also special techniques where you can use just a small amounts of another elements like tin or chromium to investigate the properties of materials, not only containing iron but other elements. And one of our new topic, it's quantum chemical calculations, and it was a group of a few people who dealt with who are still dealing with quantum chemical calculations, and from the just a small group of one of the laboratory, they grew to another lab of quantum chemical calculations, and now this lab, it's like a interdivision laboratory, so they are not related to our division directly, but now they're related to the Department of Chemistry as a whole. And one of the also perspective and very good group of group who are synthesize the labeled organic materials. They're using tritium or carbon-14 or phosphorus 32 or other biologically active atoms, and they're investigating like distribution of organic compounds in tissues, in vivo, etc. So related to geological disposal of nuclear waste, we're investigating not only the materials for immobilization of radioactive waste, but also the, let's say, the future behavior of radionuclides, or how we will migrate from their disposal if something will go wrong. And for this, to be able to model this process, of course, we need to know the thermodynamic data of radionuclides, how they interact with granites or other host rocks near the disposal, how they behave with different ligands, which are present in groundwaters, etc., how they interact with bacteria and other organic matters, etc. And one of this review of this process came to the book Actinide Nanoparticle Research, where Stepan Kalmakov, the Dean of Department of Chemistry, is one of the main co-author. Another important topic is investigation and characterization of hot particles. So again, from even after 35 years of Chernobyl accident, this topic is really hot. The hot particles is a small micron-sized particles containing the spent nuclear fuel that was released during the Chernobyl accident, or maybe from Fukushima accident, but still the behavior and impact on the human health of such hot particles is not well understood, because it's, first of all, it's not really easy to find them. They're really small. And the second, their composition is they're mainly uranium dioxide, of course, but the effect of the burn up, the effect of the presence of fission products, etc., is play a great role on their behavior, and we see that depending on the burn up of the initial fuel, their behavior can be very different. For example, one of the particles is still pure uranium dioxide, and another is uranium trioxide. That means that uranium is totally uranium-6 in these particles. That means that their leaching behavior, their migration behavior is totally different. And also, when we speak about the effect on the human health, as far as it is very fine particles, they can be how to say go with to the lung when we are breathing. And one of the studies is the study of the dissolution behavior in the simulated lung liquids, biological liquids, let's say. In separation science, as I said, we are quite successful in this topic. First of all, we used the quantum chemical calculations from that guys for modeling the, let's say, best ligands for binding the certain radionuclides. In our case, it was a separation of americium and curium, very difficult pair for separation because they're located near each other. They have similar oxidation states, similar chemical properties, and it's very difficult to separate them with conventional chemical process. But with the help of theoretical chemistry and with the help of our organic chemists, we were successful to synthesize and to develop the extraction system that was efficient for separation of such pair. And also we used the same approaches to find the best, or let's say good ligands for medical science, for radiopharmaceuticals. In nuclear medicine is not only the radiopharmaceuticals itself, but it is also the protection of radionuclides for radiopharmaceuticals. So with cooperation with Institute of Nuclear Physics of Moscow State University, with Institute of Nuclear Research in Troitsk, with Kurchatov Institute, we're developing the methods of radionuclides production. So it is investigation of which target we should use, which ionizing radiation we have to use. It can be neutrons, it can be photonuclear reactions, it can be accelerated protons, or whatever. So we try to find the best way to produce the radionuclides with the highest purity, I would say, in these words. It can be not pure, of course, because when you have nuclear reactions, you have different parallel processes, and you will also always get a number or even a large number of different radionuclides what you produced. But you can always find the conditions when the yield of your your target radionuclides will be the highest. So then when we irradiate targets, we try to develop methods for separation of all these radionuclides, purify our aimed radionuclides. Usually, again, it is like dozens of different elements in one target, and we have to separate them all to get the pure radionuclide that we are interested in. And nuclear materials and fundamental properties of actinides, again, it is investigation for finding the best solution for immobilization of nuclear waste, for also for predicting properties of the targets under irradiation, etc. And as I said before, one of the main topics of our research is the development of different systems for purification of groundwater, of liquid radioactive waste. One of our investigation was related to use of graphene oxide, and it was quite successful research. The only problem that production of these compounds nowadays is still not in such a it is not as such a mass product, but still together with US Institute of Paul Rice, if I remember correctly, we developed materials that contains graphene oxide to purify the waters. So it is a brief introduction to Moscow State University, to Radiochemistry division of the Department of Chemistry, and again welcome you at our department, at our division. And I will tell you just a few technical notes of how we will live during these 10-11 days of our school. First of all, I don't know if you recognize the rooms for men and women located on the second floor and the first floor as well. It is the first rooms if you turn right when you go down on the stairs. It is there marked, all of them. And the coffee break will be on the second floor as well. We have a Wi-Fi here. It is net as this room 308. And the password is quite simple. Just public event with small letters. Should work. We will have a lunch in our canteen. It is located in another building. We will show you during the lunchtime. We will go together there. It is located in the main building of the Department of Chemistry. You will see also the main building of the Department of Chemistry. You will have special coupons. Do you have already them? I don't know. I'm not sure. I think Andrei Putyatin, who is one of the co-organizers, he will give you just a small coupons. You will give it on the cash, on the cassa, and you will not have to pay for the lunch. Today we will have a small icebreaker in the restaurant, which is located not far from here. I think it will be more convenient if we will go again together there. It is not far away, maybe 5-10 minutes by walk. If you would like to go by yourself, it is called Durdin restaurant. And I hope it is marked on the map. With a small map. Yeah, it is on this corner, on this yellow circle, small yellow circle. Yeah. Yeah, very small map. Just to let you know about where we are now, there is a small building near the center of the map, marked with, let's say, red circle. Yeah. We are here, and the Durdin restaurant is here. So it's 1 quarter of to walk by. So what else? What else I have to say? Wi-Fi, restrooms, icebreaker, lunch, coffee breaks. Yeah.
Vladimir, a question.
Yes, sure.
The timetable.
Mm-hmm.
My lecture is at 2 o'clock Moscow
Yes.
time. Very good, thank you. Because
Yeah.
dear colleagues, I need to switch off because this week started the International School of International Commission on Glass, which is in the University of Montpellier. So I am also there. So I will need to switch off, but I will connect back to you 5 minutes before my lecture. So Vladimir, if the timetable is that one, then don't worry, I will be in time.
Okay, thank you very much. Thank you. So also, we will have now just a short test, like introductory test of you. It doesn't mean nothing, it's just for us. Please write down your name and family name. At the end of the school, we will have a final test just to see if the school was helpful, useful for you. Yeah. Yeah. Many friends of mine, then they heard that it would be a school. They asked what class of the pupils, so it's 9th class, or how old these pupils. Yeah, somehow it's like a misunderstanding of the meaning of school. Yeah. And as far as it is school, we have to check if the education was successful. Just simple questions. The final test will be a bit more difficult. Так, все здесь, да?
И потом сделать просто. Значит, он приедет в течение часа.
Sorry for interruption. Every day we will need to sign up for the form, just that everybody is here. So. Nice. Finish.
понимаю, что будет тут. Так что ты мне просто покажешь место, где все это будет лежать.
Вот эти? Я тебе могу просто...
А что я сейчас даже заснуть никуда не могу.
Ну
Да,
все
да, я
равно
полежу.
нужно убить.
Я тебе не даю.
Так, что там делать?
У нас 10-минутный перерыв.
Have you been to Antalya 4 or 5 years ago?
Yes,
with the
yes.
Moscow State University members. I was also in
Agdenis,
Agdenis,
yeah.
I remember, but I cannot be sure. How are you?
Good, thank you. And you? How is going on in Agdenis University?
Actually, that project is
Then we should start with them. Okay, and our first lecture will be on the basics of nuclear fuel cycle with a bite of radioactive waste taste, let's say. I don't know the basics of your education of all of you, so maybe some lectures, some parts of the lectures for you will be very simple, very obvious, but not for everyone. Yeah, okay. And let's start with the question about the situation with the energy in the world. And this is a night map that was taken from the International Space Station by NASA. And as you clearly see that the distribution of the energy consumption is very non-homogeneous around the world, and the countries like countries in Africa, in some countries in Asia, countries in Latin America, they will the demand of the electricity or the heat production will grow in these countries. Certainly, these are developing countries, and that means that the need in energy will increase without no questions. And where we can get this energy, of course, it can be different types of sources. But we will talk about the nuclear energy, because nuclear energy has a lot of benefits. And so, first of all, it is a significant reduction in CO2 production, in CO2 emissions. There are several articles in different magazines that, let's say, debate on the CO2 emissions from nuclear energy, nuclear power plants and wind turbines, and still there is no clear answer. So one of experts says that wind turbines win, another that nuclear power plants win. But nevertheless, it is clear that the CO2 emissions in the case of nuclear power plants is very low, and much lower than in any kind of energy production, maybe except of wind turbines. It is a decrease in those laws, those of ionizing radiation. It can be very strange, because nuclear power plants use radioactive decay, and ionizing radiation should be produced in nuclear reactors, and it is produced, but a lot of safety systems, a lot of barriers makes it almost impossible for ionizing radiation to go out from the nuclear power plants. And the main source from among different types of energy production, the main contribution to the population dose is the coal power plants that use coals, because natural radionuclides that are present in coal, they are concentrated during coal burning in ash, and ash goes to the air. And these natural radionuclides that are concentrated in ash, they goes around the power plant, and the dose loads around this coal power plant is much higher than just a natural background in this area. And nuclear power plant has almost no emissions of radionuclides. So the main emissions may be inert gases like xenon or krypton. These gases with short half-life can be released in some cases from the nuclear power plants. All this makes price for electricity a bit lower than for conventional power plants, but again, it depends how to calculate it. Because these calculations, as I understand, didn't account the construction of final disposal of radioactive waste, because there are still no final disposal of a high-level radioactive waste in the world, and it is hard to count this construction in this price. But nevertheless, even if it is lower or the same, the price for electricity is comparable, let's say, with the conventional sources. But the important part of the cost of the electricity generation is that the impact or contribution of the cost of the fuel itself in the whole cost or the whole price of electricity production is very low for nuclear energy. It is around 5–10% of the cost of electricity generated by nuclear power plants, because the main cost in the case of nuclear power plants is coming from the construction of nuclear power plant itself. And the cost of the fuel will be around 5–10% of the whole price. But it is not the case for conventional sources. In the case of hydrocarbons, oil, gas, the contribution of the fuel price can be up to 75% of the whole price. That means that if there will be any deviations in the price of the fuel, the deviation of the price of electricity generated will be also differ. In the case of nuclear power plant, even if the price for uranium will go up to, I don't know, twice, the price for electricity will increase slightly. That is not the case for oil or gas sources. And the fuel reserve, I mark this in the very pale gray color, because all these forecasts for I don't know, reserves of reservoirs of fuel for oil and gases, when I was in school more than 20 years ago, it was written in the textbooks that there will be only 20–30 years for oil and gas, but still they are here, and the forecast, the new forecast, that it will last for more than 50 years more. And so all these forecasts, how to say, they're changing with time. And I personally cannot believe in these numbers. But if we will read in different expert opinions, we can say that, okay, the reserve for fuel in the case of nuclear power plant is larger than for hydrocarbons like oil and gas, because we have uranium, we have millions of tons of thorium. That is also a possible source for future nuclear energy generation, etc. So there are quite a lot of benefits for nuclear energy. Also, if we compare the energy capacity of the nuclear, of the energy in the case of nuclear power plants, or the still developing thermonuclear generation, it is 100,000 times more dense energy capacity for nuclear production than for conventional production. For example, it is a comparison that 26 milliliters of nuclear fuel can produce the same amount of energy as 26 cubic meters of gas. So again, we can produce energy from the smaller volume of the fuel. Again, if we are speaking about the ecological impact of different types of energy sources, one of the aspects is the area that we used for energy production. And in the case of nuclear power plant, we will need around 2.5 square kilometers for one nuclear power plant with the energy production of 1 megawatt. The same amount of energy will be produced by wind turbines that will occupy the land 360 times more. It is around 400 something wind turbines that we will need to produce the same amount of energy. And if we are talking about the solar energy, then it will be the land occupied will be 75 times higher. It is about 3 million of solar panels. Anyway, in Rosatom, there is a concept that is called green square that put 4 types of energy productions together as a, let's say, green source of energy. It is wind turbines, solar energy, hydro power plants, and nuclear power plants. It is again safe, we cannot say that something safe 100%. Even when we are going by bike or using, I don't know, elevator, it's not 100% safe. That means that nuclear power plants, they're also not safe for 100%. But we can say that every generation of nuclear power plants have much higher safety barriers, so the probability of any accidents is decreasing. But it will be never 100% safe, as nothing 100% safe. But we can say that it's more clean than other sources of energy. But again, nothing is perfect, and we have radioactive waste that arise from nuclear energy production. So what is the radioactive waste by term? First of all, it is material that contains or is contaminated with radionuclides. But as far as it is waste, then we can say that this material is no longer in use in current technologies, at least. But it's not the full definition, because if we will talk even about our bodies, it's maybe not the perfect example, but many people remember it clearly. For example, every of us contains radionuclides, natural radionuclides like potassium-40, tritium, carbon-14, etc. So we are radioactive. All materials that are around us are radioactive. When we are dying, unfortunately, it will happen. Our body will no longer in use. So it's material with radioactive radionuclides, but no longer in use. But it's still not a radioactive waste. So the full definitions will include that radionuclides should be at concentrations higher than the clearance level, and this clearance level, when we can tell that this material is no longer radioactive waste, these levels are established by governments in certain countries. It depends totally on the regulatory body in a country. So I think it's clear now. And but let's say, the benefit. Okay, so now about nuclear fuel cycle. The nuclear fuel cycle, it's a whole chain that starts with uranium mining. So we extract uranium ore, we extract uranium and purified it. And then we convert uranium to uranium hexafluoride, enrich uranium, because thermal reactors need more uranium-235 in nuclear fuel than natural uranium contains. Then they fabricate fuel from this enriched uranium. Then they produce electricity in nuclear power plants, electricity and heat. Then the spent nuclear fuel that is no longer in use in these nuclear power plants goes to storage. And then there are two ways how to deal with this spent nuclear fuel. Either we directly dispose it, and it is called open nuclear fuel cycle. We do nothing with spent nuclear fuel, just put it in the canister and put it in the final disposal in a deep geological repository. Or we reprocess, that means we extract the valuable components like uranium and plutonium. We can produce the new fresh fuel from this uranium and plutonium and put it again at nuclear power plant. And in this case, it is closed. It is called closed nuclear fuel cycle, because we use it again. There are pros and cons for both of these cycles. Nowadays, honestly, from calculation, economical efficiency, unfortunately for me personally, the open nuclear fuel cycle is still more efficient from economical point of view than the closed nuclear fuel cycle, because we don't need to build a reprocessing plant. We don't need to produce additional waste from this reprocessing. We put radionuclide that are already in solid form, in stable form, and we put them in good condition, let's say, directly in the disposal. But as far as the reserves of nuclear fuel are not infinite, at some day the refabrication, reuse of uranium and plutonium from the spent nuclear fuel will be more efficient from economical point of view. In Russia, it is, let's say, dictated that we have a closed nuclear fuel cycle. We have, or at least a partly closed nuclear fuel cycle, and we have a national program now that is called Prorыв or breakthrough. The main aim of this program is to close, totally close the nuclear fuel cycle. So next. So it is more fashionable picture of the same cycle that I took from the Rosatom website. So you will have all the presentations, so you can see more nice pictures maybe. But I still prefer this clear picture because it may, from my point of view, it is more clear for understanding. So where the radioactive waste generated? In every step, from mining to disposal, in every step of the nuclear fuel cycle, we produce a radioactive waste. So, and come on, I'm too far away. Yeah, and one of the benefit, if we can say it, of the radioactive waste is the radioactive decay. With time, radionuclides decaying. That means that the radionuclides transform to another radionuclides until the decay chain reaches the stable nuclide. That means that the hazard of radioactive waste is finite. At one point, the hazard of radioactive waste will be not higher than the initial uranium ore. So that means the natural background. And this is comparison with the hazardness of conventional waste, let's say, like mercury or chromium, so heavy metals. Yeah, and we see that advantage or benefit of radioactive waste, that with time its hazardness is decreasing, but the dangers of these stable elements will not decrease with time. So that's the point that many people are forgetting then speaking about the radioactive waste, that radioactive waste will decay, and then let's say normal waste will not decay never. And let's now look on the different stages of nuclear fuel cycle. And first of them is the mining or extraction of uranium ore. There are at least 3 types of uranium ore extraction from Earth. It is carriers, when it is open carriers, huge carriers. It can be mining, so it is closed carriers, let's say, and underground leaching. Of course, underground leaching is the best way for extraction of uranium, but unfortunately, it can be applied not for any uranium ore. Yeah, it should be special conditions like permeable layer where uranium ore is located, with horizons that are not permeable for water. So it's like a lens where you put water and it goes only through this lens. So you put extraction, leaching liquor. It's normally sulfuric acid solution. You leach the uranium with other metals, of course, and then you take all these solutions out. So you have no oops. We'll clean. Just don't step on it. So the underground leaching is the best way to extract uranium because there is almost no impact on land. After 10-15 years of exploration, when the leaching is finished, the land will become will remediate itself, so it will reach the initial state, let's say. Unfortunately, when we use carriers or mining, we need then a special process to extract uranium from the ore. So we are leaching uranium from this ore that is that forms like mountains, and we put solutions on the top of the mountains. It penetrates the solutions of sulfuric acid penetrates the mountain of the uranium ore and extract uranium, and then this liquor is going to the plant where uranium extracted by conventional liquid extraction, and then produce the yellow cake. So in this case, we produce quite a lot of tailings, and it is from my point of view, it is one of the most dangerous nuclear waste, because it usually stores unsecured. It's of course there is special lining under the tailings that keeps all the solutions that goes through the tailings away from the underground waters. But to be honest, all these linings are quite old. It degrades with time, and sooner or later all the contaminated water that penetrates through the tailings will go to the nearby rivers or underground waters. And even if we extract uranium from this ore, it still contains quite a lot of decay products of uranium. First of all, radium-226 that produce radon gas. So that means that near this territory, we have a much higher exposure of radon gas. And for the information that by the World Health Organization, the radon is suggested, or not suggested, is determined as the second second reason for lung cancer. So the first is smoking, of course, and the second is radon exposure. So that means that near this uranium tailings, the population is under a huge risk of higher probability, higher risk of lung cancer. And of course, all these radionuclides like polonium, thorium-230, and all the decay products will go to groundwaters. And again, even if it is natural radionuclides, the concentrated radionuclides, they possess very high hazard danger for human health. So it is first radioactive waste that is produced in the whole nuclear fuel cycle, but it's not the safeties or how to say it, radioactive waste. So then we convert the yellow cake that is uranium oxide to uranium hexafluoride through several steps of preparation. Uranium hexafluoride has very good properties because it's sublimate. That means that it goes from the solid phase to the gaseous state without melting. So that calls sublimation. And the temperature of sublimation is quite low, so it's only 56 Celsius degrees, and that's why it is used further for the uranium enrichment in gaseous states. During the production of the uranium hexafluoride, of course, there are again liquid radioactive waste that are generated from the uranium purification process, and also uranium hexafluoride as well as like defected parties of uranium hexafluoride stored also near these plants. Then we enrich uranium hexafluoride with uranium-235 isotope for thermal reactors, and there are two main technologies. It's a gas diffusion method that is used in USA, and the gas centrifuge that this technology used in Russia. Yes, and of course, gas centrifuges they have more benefits, especially new technologies. The centrifuge can work, I don't know, 30 years without any problems, and from economical point of view, the gas centrifuge are more reliable, and everything is clear from physics, but where the radioactive waste? First of all the equipment sooner or later become contaminated with uranium hexafluoride, and it goes to the fine holes of the equipment and accumulated with years. And again, when we have to decommission this facility, we have to handle this whole equipment contaminated with uranium. Another point is the hexafluoride itself with depleted uranium. And I don't know, maybe some of you heard this news, the rumors, then depleted uranium hexafluoride came from Germany to Russia. It was a lot of debates, even some protests from this against this fact. But is it really a waste? As I told you before, that the waste is a material that is no longer in use with current technologies, and with current technologies, some of the depleted uranium is really no longer in use because there are no economical benefits from taking this depleted uranium hexafluoride and trying to enrich it again. But technologies are developing, and this gas centrifuges is still the efficiency is still increasing with each generation step, and that's why this depleted uranium hexafluoride can be used further. First of all, in enrichment procedure, in enrichment processes, and the second in the fast reactors. And that because uranium-238, that means depleted uranium, contains mainly uranium-238, and uranium-238 can be used in fast neutron nuclear reactors. So that means that, yes.
Depleted uranium is kind of nuclear waste, or how can you categorize waste?
It depends on country again, because every country has their own law on categorization of radioactive waste. This depleted uranium in Russia is not waste. So
that's why you can accept them too.
Yes, because the depleted uranium, depleted hexafluoride of uranium that came from Germany has a content of uranium-235 high enough to be used in enrichment process, even with current technology. So that's why it's not a radioactive waste. It's a radioactive materials, but it's not waste. Yeah. And some of them, that is, but again, that is the uranium hexafluoride that came from Germany was used in enrichment process. So it is possible to enrich it more.
No, I mean the output of enrichment process.
Yes. It's a byproduct of the enrichment process. Yes. Of course, if we take natural uranium with the content of uranium-235, let's say 0.7%. Yeah. It's in natural uranium. If we enrich some part of this uranium, then other part will be depleted. And as far as content of uranium-235 in natural uranium is very low, when we enrich, even when we produce a small amount of enriched uranium, we produce a huge amount of depleted uranium. That's why there are thousands of tons of depleted uranium hexafluoride stored in different containers. It's one of the example how it is stored. New containers will be more beautiful, but still with time they're corroded, and it's just a question of how to store them safely. Because depleted uranium hexafluoride is more dangerous as a chemical, not as a radioactive material. Yeah, it's very toxic. Yes. But again, it is a source for a future fuel. So it is not waste even in current technology. In Russia, we have reactors with fast neutrons in what the city, Beloyarskaya nuclear power plant. No. It's in Ural, in Sverdlovsk area. I forgot the name. Zarechny city or town. It's not a very big city. Yeah, and they have 2 reactors, BN60, BN80, that are working with fast neutrons. And fast neutron reactors can use the depleted uranium as a fuel. So that's why it is not correct to call this material radioactive waste. It is a radioactive materials that are under storage process, let's say, but for future application. So nuclear fuel fabrication. So when we enrich uranium hexafluoride, then we convert it back to uranium dioxide. It is now the main form of, yeah, you have a question, sorry. I don't have graphs here, but so you have to trust me. But I can try to draw it. There is a parameter that is called nuclear cross section, and that means the probability of nuclear reactions. It is the energy of neutrons, and the highest. Yeah, we will talk now about uranium-235 and uranium-238. Yeah, about the cross sections. But again, nuclear reactions can have different nature. We will speak about the nuclear reactions of fission nuclear reactions. Yeah, when it produce a lot of energy, and the highest cross section, the highest probability of this reaction, of course, will be when the neutrons have a very low energy. Why? Because if we consider a nucleus as a sphere, let's say, and neutron also as a small sphere going through this nucleus, if it will be very fast, it will be just go through this and causing no reactions at all. Too fast. Neutrons need some time to be inside the nucleus to be able to produce this fission reaction. That's why the slow neutrons with low energy will cause more fission reactions than the fast neutrons. So in any case, the probability of these cross sections when neutrons have low energy will be the highest. Yeah, with when energy will increase, the cross sections will decrease. Yeah, there are some oscillations, resonant lines, but I will not go in detail. The main pattern is that the cross section will decrease with the energy increasing. For uranium, it is for uranium-235. Uranium-238 will not have the fission reactions with the slow neutrons, thermal neutrons, because it will just capture neutrons, go into uranium-239, neptunium-239, and finally plutonium-239. Yeah. It will be the main route of the for uranium-238, but in fast region, it will be a small increase in the cross-section reactions of for uranium-238. I don't know the nature of this effect. Maybe the physicist will say it is more clear. But in this region, the cross sections for uranium-235 and 238 will be more or less the same. That means that in this region, it doesn't matter what we use, uranium-235 or uranium-238. And that's why in reactors with fast neutrons, we can use uranium-238, uranium-235, plutonium-239, doesn't matter. It can also, we can also use the americium nuclides and others. So region of fast neutrons is very promising, but the technology is very difficult because when nucleus is decaying, the neutrons that are produced, they have very high energy. Yeah, and to slow down them, we need to use a special moderator. In modern reactors, it's just the water. Water decelerates neutrons very efficient. So they, in initial step, the initial neutrons, they're very fast, and water slow down them. That's why we use water as a moderator, as a coolant, and use uranium-235. The technology, not simple, of course, but it's understandable. And to use fast neutrons, we have to use another coolant. We cannot use water. Yes. Water, no. We use liquid metals. It can be sodium, as all fast neutron reactors that existed at the moment, they use sodium. It was French reactors, it was Japanese reactors, and Russian reactors. All of them used sodium as a coolant. We don't need any neutron moderator because we need fast neutrons. And nowadays there are project, at least in Russia, to use lead, or they have tactic with bismuth. Yeah. Another possibility is to use gases, carbon dioxide, argon, maybe nitrogen. Nitrogen is not the best option because it will be activated by neutrons, so not very good. Yeah, carbon dioxide and argon, or helium, of course, helium. Helium, yeah. Graphite. Yes. Maybe it depends on the construction. I'm not a reactor physicist. I know. Yeah. Yeah. Okay. Yeah. So the answer why we can use uranium-235 or 238 is just in fundamental nuclear physics of this process. Yeah, sure. In this through these reactions of neutron capture, we can also produce plutonium-239. Yeah, no question. Yeah. And plutonium is excellent source of nuclear fuel. It has higher nucleus cross sections, and everything is good with that. Only problem with plutonium that uranium you can handle it with just your hands without any additional safety procedures. Plutonium is another story. Yeah. So, and nowadays the main form of fuel is dioxide of uranium dioxide or mixed uranium and plutonium dioxide that it's called MOX fuel, mixed oxide fuel. There are different other forms that is used in research reactors, in some reactors for transport vessels, like marine reactors, etc. They use different types of uranium, different forms of uranium. It can be metallic or alloys with gallium or whatever. It can be carbide fuel, and nowadays the nitride fuel is it's already not under development. There are already fuel rods that contains uranium nitride as a fuel, and it was tested in these fast neutron reactors. And yeah, as I told you, that when it is just the uranium that came from enrichment plant, we can just take it with hands, maybe in gloves, just to avoid contamination with heavy metal. Uranium is a heavy metal, toxic again, and that's it. And wear the mask just to avoid inhalation of uranium. But it's not very radioactive. Yeah. But after when we produce this fuel, there are some pellets that are defected with cracks or with non-homogeneous distribution of elements. In some pellets there is a gadolinium for some purposes, and the distribution of elements can be not very homogeneous, and it is defected. And then it goes again for dissolution, purification, and all this process. That means that even if we have, let's say, clear uranium hexafluoride enriched, and we produced from uranium F6 uranium O2, it's a rather simple process. Even in this procedure, we will generate radioactive waste anyway. And the liquid radioactive waste that are produced in this plant, they have quite difficult or complex composition because all the streams from different processes goes to one barrel, and the composition becoming very complex. And yeah, how the problem is to treat this radioactive waste. Then we have nuclear power plant with different design, PVR, VVR, other type of reactors, but the main construction is that we have a reactor itself that generates a lot of heat. We have a coolant. We have a second circuit of coolant that produce steams and generate electricity, etc., etc. Again, nuclear power plant is more or less hermetic. In normal operation should be no release of radionuclides, but nevertheless there are still contamination of water that is circulated, and to purify this water we use the ion exchange resins, and the main waste that is radioactive waste that is generated in nuclear power plants is ion exchange resin. So it is the same ion exchange resin that you use in your filtration system for tap water, so more or less the same resins, but the problem is that almost all of the accumulated resins, they are still stored at nuclear power plants, and the storage has a finite volume. So sooner or later, we should treat all these ion exchange resins. And nowadays, it's a big discussion on the technology of how to treat it. Every nuclear power plants in Russia has its own solution. So there is no unified solution. So it's again a problem for national operator who accept all this waste, because they're coming in different shapes and forms, and that's really a problem. When we are talking about the technology to treat radioactive waste, we also have to remember the criteria for acceptance, and we cannot use any technology that we like. We have to take technology that will generate processed waste in the form that is accepted. Huh? Yes, it's resin, it's organic, and there are a lot of problems. No. Yes, so one of the technology, of course, burn, but how to deal with ash? You have to have a lot of systems that will purify the gases that are going. So it's a lot of problems with that. Also, how to burn it? There are different techniques. So it's not a simple question as it looks like, but yeah. The nuclear fuel itself, after working in the nuclear reactors, calls the spent nuclear fuel, and it becomes a very complex system, because it contains almost half of the periodic table of elements, going from zinc to plutonium and even californium in some cases. And all these elements, of course, have different chemical behavior. They form different compounds that have different thermal conductivity, different volume, etc. So you see these dots in fuel. It's a pathways for gaseous fission products, etc. So spent nuclear fuel is very complex systems, and sooner or later, due to accumulation of neutron poisons, due to decreasing of thermal conductivity, decreasing of mechanical strengths, it becomes no longer reliable to use in nuclear power plants. So this spent nuclear fuel goes to storage, first of all, in cooling pool, and then goes either to reprocessing, because more than 95% of the spent nuclear fuel is valuable elements, uranium and plutonium, what we can use again. First, this spent nuclear fuel is stored in storage pools to that short half-life, short-lived radionuclides will decay, and the dose from this spent nuclear fuel will decrease, and we can use it. We can handle it in water solutions. Spent nuclear fuel is not always radioactive waste. If we can extract valuable components, it is just radioactive materials. Or in open nuclear fuel cycle, we can say that it's radioactive waste. Then the story is short. We stored it for a certain time and then go put it in the final repository. The only final repository that will be most probably in use soon, in 2025, is in Sweden or in Finland. Sweden. Yeah, they are very close to each other, and not only geographically, but also the status of the final repository. So Sweden will be probably the first country that will operate the final repository for for spent nuclear fuel. So they will not reprocess it. Spent nuclear fuel is a waste. In our country, it's not a waste. We will reuse it, and already reuse. And what other benefits of reprocessing of spent nuclear fuel is that we can decrease the long-term dangerous or long-term radiotoxicity of this material. So if we'll look on this graph, maybe most part of you know this graph. So this red line is the total, let's say, specific radiotoxicity of the spent nuclear fuel. Yeah, how it decreases with time. The time scale is not a linear scale, but logarithmic scale. It is important because here's number 10 to 6. That means millions of years. And we see that even after 100,000 of years, it still will be dangerous with the radiotoxicity higher than natural uranium. That means very dangerous. But if we extract plutonium, we extract americium, curium, and other long-lived radionuclides, and it will be only short-lived fission products, this green line. That means that after, let's say, 300 years, it will reach, the radiotoxicity will reach the level of natural uranium ore. That means it calls radioecological equivalent. That so we put in the underground the same activity as we took from the Earth. Yeah? So it's radioecological equivalent. So to do this, we have to extract all the plutonium and all the actinides, let's say, and some other fission products like technetium 99, iodine 129, and store them separately. But again, even if we separate all these actinides of all these long-lived radionuclides, we still have them. Yeah, so it's not the real solution just to separate them. But the real solution is the transmutation of these elements. And again, it will be possible when we will use fast neutron reactors. All these radionuclides will transmute. That means that they will either undergo the fission reactions, like americium, for example, and neptunium, or they will convert to another radionuclides, even probably stable. Technetium will convert to ruthenium 99, that is stable nuclide. So the transmutation means that we either produce radionuclides with shorter half-life, or we produce even the stable elements. And again, it will be possible in reactors with fast neutrons. Yeah, this is BN reactors that is currently under operation, and this is a design of this new breast reactor. It's called breast because it is a reactor with fast neutrons. Fast on Russian is bыстрый, B, so it's bыстрый reactor. And east, it's with natural safety. In Russian, again, it's естественной безопасности. Естественный. So this abbreviation breast means the fast reactor with natural safety. Because if something goes wrong, the lid will just not melt, but another process. Freeze. And so all the reactor will be sealed and nothing will go from this reactor. Again, if we separate and transmute all the long-lived radionuclides, we significantly reduce the volume of highly active waste. This photo I took from a presentation of one of the Indian guy during one of the conference. I don't remember the name, so there is no link. But I really like this picture where it is clearly shown the volume of high-level waste generated by conventional nuclear energy. It is still not very high, you see. So the volume of high-level radioactive waste is quite small. And this small diamond in the ring of the lady is a really tiny amount of the high-level radioactive waste generated if we will separate off the long-lived radionuclides and transmute it. So it's really impressive, and I think it is the future. But how to separate all these radionuclides? And the main technology that is used in France and Russia, in UK, is the solvent extraction, or liquid extraction, solvent extraction. It is the redistribution of elements between two immiscible liquids. It is used for not only for nuclear application, of course, but also for food application and many other applications. And the main process that was developed more than 50 years ago and still under operation is PURIX process. That means plutonium-uranium redox extractions. And it is rather simple process. One of my teacher always have joked that even so I need just kerosene and a bit of TBP to reprocess all the spent nuclear fuel in our country. So that means that any I don't know pupil, any student can do this separation. Chemically, it's really a simple procedure. First of all, we dissolve spent nuclear fuel in nitric acid. Then we add this organic solution containing tributyl phosphate in kerosene. Uranium and plutonium goes to the organic phase. Then we add a bit of reductant. It can be iron 2, ascorbic acid, or even uranium +4. The main purpose to use a reductant or reducing agent is to reduce plutonium-4 to plutonium-3. Plutonium-3 is no longer soluble in organic phase and goes to water aqueous phase. So it is back extracted to aqueous phase. And uranium still remains in the organic phase. So we separate quite easily uranium and plutonium. So at the first step, we separate uranium and plutonium from all the fission products. Only some neptunium, maybe technetium is contaminating this solution, but all the cesium, strontium, rare earth elements, whatever, are remaining in aqueous phase. Then organic phase, again, with a simple procedure with reducing agent, we wash back the plutonium +3, and uranium is in organic phase, and then uranium 6 we back extract with just water solution, just almost not pure water. It is really weak acid solution, and that's it. So it's really simple procedure that was developed more than 50 years ago and still under operation. But there are plenty of different processes, different molecules that are developed for extracting or separation americium, curium, certain fission products like cesium and strontium together or separated. So there are plenty of processes under development in different countries, and yeah, large number of them. But all this process, all this liquid extraction produces a huge amount of liquid radioactive waste, and there were several options that nowadays looks very strange and impossible. Many of this liquid radioactive waste were just put it into rivers or ponds, open ponds, and it was several accidents with these open ponds when in dry weather, like not like this, in hot summer, the level of water, how it's called, water mirror in Russian, I don't know if it is correct, is reducing the surface area of these ponds. And that means that the sediments are becoming open to the wind, and all this dust with radioactive materials, it's highly radioactive dust, goes with wind to the surrounding territories, and it was really bad. It not very good seen here, but there are several villages that were evacuated due to this process, due to the contamination of the river, water river. And so it was in Russia. Nowadays it is Lake Karachay that is located in city Ozersk in Chelyabinsk region. Nowadays it's no longer exists. It was decommissioned and filled with soil, so there is no open water anymore to prevent this distribution of radioactive dust. And this is the example of US tanks filled with liquid radioactive waste that is again located just in, even if it is closed cementitious construction, nowadays part of them degrade, and some of the radioactive waste leaked from these tanks and go into nearby Savannah River in the USA. So the situation is very bad, not only in Russia, but in other countries like USA, UK, France, and other countries that are dealing with radioactive waste, with high level radioactive waste. So the situation is bad, but nothing is impossible. Nowadays, there are quite a lot of technologies that are developed for remediation of the territories, for preventing the radionuclides migration with underground waters, or with other. On Monday it will be a lecture on barrier materials, so it will be more information about these different barrier materials. So yeah, and for the final disposal of high-level radioactive waste, even if we transmute most part of the long-lived radionuclides, still some of them will exist, because there are no miracles in nuclear physics, almost no. And some of the nuclides will not be transmuted, some even nuclides, and they will accumulate it during the process of transmutation. And so anyway, we will need to have a final repository. It will be much smaller than we need today, but still we will need it. And there is a multi-barrier concept accepted in any countries who are planning to build this final repository. And the multi-barrier concept is like this Russian doll. We have metrics stable metrics that are resistant to water action, to radiation, to thermal, to whatever effects. This matrix is we put in a container. Again, It can be stainless steel or copper-like in Swedish concept. So it is stable container but that we put underground on a depth like 400, 500 meters. And we fill the gaps between the container and the host rocks with the barriers, the special barriers, buffers. And yeah, all this system located underground on like 400, 500 meters in depth. So it looks like really safe concept, but every of this step, every of this component have to be studied, investigated, and approved or confirmed its safety. In Russia, there is also was selection of the final disposal, and it was chosen. It will located in Krasnoyarsk region. Krasnoyarsk is a very big city with the more than 1 million citizenships, and the final repository will be located in the city of Zheleznogorsk. That is located around 50 kilometers from the Krasnoyarsk, and yeah, it will be 500 in depth, and a bit different design of the repository. In Swedish concept, you see there will be, or already is, like a rod that is going like a spiral from top to down. In Russian concept, it will be 3 wells with elevator. It will be 6 meters in diameter each well. So one will be for transportation of containers, one for personnel and equipment like cars or whatever they will need, and the third one is for ventilation and some safety systems. Underground, it will be again tunnels with different branches. Again, we have this multi-barrier concept, stable matrix. Nowadays, only glass is considered as a final stable form of the high-level waste. It's a canister. In Russian, again, it's stainless steel. And the buffer materials, in Russia, it's bentonite clays. And all of this is located in gneiss massive in the depth of 500 meters, let's say. But all nuclear fuel cycle is not the only source of radioactive waste. There are several other sources like medicine, of course, but the again advantage of this radioactive waste that they are short-lived. So after, let's say, 1 month, you don't care about this waste. Industry and research and some medicine also equipment dealing with source of gamma rays like cobalt-60 or cesium-137. Yes, this sealed radioactive sources, another type of radioactive waste, and there are another concepts of how to deal with them. Of course, it's research, like even in division of radiochemistry, we are working with radioactive materials, with solutions, and we generate not a lot of waste, but some volume of liquid radioactive waste, and our national operator once a year took them from us and put it in interim storage. It is food and agriculture applications. Again, it is sealed gamma sources like cesium-137. Again, it is it is naturally occurring radioactive matters. As I said, this tailings of uranium mining, for example, but it's again nuclear fuel cycle. But when we are speaking about rare earth production. Again, rare earth minerals contains quite a lot of thorium and uranium elements and their decay products. And when we concentrate rare earth elements, we also concentrate natural radionuclides. And this is an example of White Mountains that is located not far from Moscow, around 30 kilometers or something like that, near the city Voskresensk. This is a byproduct of phosphoric acid productions from apatite. Apatite, it is the phosphate minerals, and from phosphate minerals, by addition of sulfuric acid, they produce phosphoric acid for agriculture applications. And in this phosphogypsum, so apatite is calcium phosphate, and after treatment the gypsum is produced, and this gypsum contains first of all rare earth elements, a bit, about 1-2%, but also uranium and thorium in this White Mountain. And the waters around this White Mountain contains higher concentration of uranium and thorium than they should contain. So it is again norm naturally occurring radioactive matters that are coming not only from nuclear fuel cycle, but also from let's say non-radioactive production, like rare earth elements, phosphoric acid, and even oil and gas production, because pipelines, they accumulate quite a lot of radium inside, and it is also a problem. Not all of oil companies want to admit it, but it's really a big problem. Nowadays, all these pipes, they are just yeah, they accumulated on the ground, and that's it. So, but it's not very good. The only advantage, or how to say, the only excuse for that all this storage is allocated far away from the populated regions, but still, okay. Of course, accidents, yeah. So, as a brief conclusions, radioactive waste, they're produced in any activity using radioactive substances. Any step of using radioactive material will produce radioactive waste. Even norm, when we don't use directly radioactive substances, you can produce radioactive materials. Characterization of or categorization of radioactive waste will be in further lectures. Spent nuclear fuel is not always radioactive waste, because we can extract valuable components, and the reprocessing of spent nuclear fuels can reduce not only the activity, but also the long term of the potential hazard of this material. Currently, we use only the Purex process for reprocessing of spent nuclear fuel that produce a huge amount of liquid radioactive waste. And we have to remember about the multivariate concept when we are speaking about the final repository. Again, what I would like to say that, and to remember that there is no operation with radioactive materials where you will not produce radioactive waste. Every step you will get a radioactive waste. Yeah, and that's it, I think. Yes, for this lecture, it is the final slide, and now you will get these small coupons from Olga. I think she's here. We will find her anyway. You will go to the lunch with Olga. She will show you where the canteen is, and we will start at 2 p.m. So please be here. Okay, so now we can go. Thank you. Yes, I can close the room. Yes. You can put all your stuff here. Yes. There's a green light, and that's it. And ask the question. Михаил Иванович, добрый день еще раз.
Да, здравствуйте, я готов.
Так, ну, наши пока собираются.
Хорошо, я пока экран поставлю и отрегулирую все.
Ага. Сейчас, так, я вам разрешу, по-моему.
У меня, по идее, должно быть. Сейчас посмотрим.
Ага.
Появилось?
Да-да-да, о, запускается, все отлично.
Хорошо.
Мгм. Ну,
Ну,
все, так,
ждем.
5, да, подождем. Я думаю, потом между лекциями небольшой перерывчик, да, чтобы...
Обязательно, он предусмотрен.
Да, все, хорошо. Так. Just 1-2 minutes, everybody is going upstairs from the coffee break. Small. So, Professor Ojovan, I think we can start now.
Okay, thank you. Vladimir, thank you. Is the lecture recorded as it was in the morning?
Should be.
I'm just asking.
Just a moment, I will check. I'm not sure. Just a moment.
But this is, Vladimir, your business. So do I?
Yeah. You can start, and I will check that.
Okay. Okay. So you can see on the screen the title of my lecture. Classification of radioactive waste and source categorization. But these sources that are here are not the sources that just Professor Petrov has explained to you, the sources of radioactive waste. These are specific sealed radioactive sources. The devices which have a very high radioactivity kept in a very small volume. So in some countries they are termed even pencils. I know that, for example, in India they are called pencils. So we have, as participants, you are now all students. So some students should be from India. So they are called in India pencils. So these source categories. Oh, colleagues, we are recorded now. So let me push here, continue. Okay. So we are recorded. Good. So okay. So you see then my name here and my current affiliation, and also you see this picture. This is the cover of the journal, which is owned by Wiley Hidavi. It is an open access journal of nuclear industry. It is called Science and Technology of Nuclear Installations. So I'm the chief editor-in-chief of this journal. But my immediate past, a couple of years ago, I worked for International Atomic Energy Agency in the Department of Nuclear Energy. So I'm introducing myself here. So these are the topics that I'm going to introduce to you gradually. So my intention is first to explain to you what are sealed radioactive sources and their categorization system. For the reason that these are very dangerous materials that sooner or later they become radioactive waste and then need to be managed, and the operational safety, it is based on categorization into the 5 categories, and these categories should not be intermixed with the notion of classification of radioactive waste. So in dealing in managing radioactive waste, in any operation, work with radioactive waste safety, of course, is the question of primary importance. Operational safety, it's one thing. It is what do we do? Everything should be safe. But in radioactive waste management, then we have got long-term safety. When we leave the material for a long time, either to be stored or we dispose it off. And then it's actually a kind of passive safety. And these are different things, operational safety and long-term safety, which is rather passive safety. We are not doing anything, but we rely on the barriers that we created during the operational phase. So because of that, I will start with the sealed radioactive sources, but first the background. So we will make a break after this lecture, some 15 minutes. And after that, I will explain to you, there will be 2 lectures, one today and another tomorrow, on the standards, international standards in dealing in the management of radioactive waste. So at the moment, I just introduce you here. You see the cover of an IEA safety standard, which is called General Safety Requirements Part 3.
Я
But
говорил, это очень недалеко, да.
historically, this document started to be named Basic Safety Standard. Basic Safety Standard. This is the basis of doing everything in a safe manner. How it is required internationally, on international level. So most of the national standards that you have in your countries are based on this basic safety standard. So at the moment, here, it is the definition of radioactive waste. Very important, the definition of radioactive waste. So it says that for legal and regulatory purposes, material for which no further use is foreseen. So it's a material that we don't need it, and because of that is the waste. But the waste doesn't mean radioactive waste. So it contains or is contaminated with radionuclides at activity concentration greater than clearance levels, as they are established by regulatory body in each country. They are recommended internationally, but in your country you have your clearance levels. And only if in the material which is waste, they are exceeded, then this is radioactive waste. And among radioactive waste can be also sealed radioactive sources, which need special attention. Because of that, I will explain in more details about sources. So I put here also a cover of a book. It's a thick book, which gives a kind of overview. It is that one, of the situation with radioactive waste management and contaminated sites cleanup in different countries. And something additionally I will note later. At the moment, let's look to this picture. So where is my laser pointer now? So we have nuclear materials, the materials from which some radiation is emitted, or the material that contains higher than clearance levels radionuclides. And we have this picture divided in 2 parts. In this part, it is written useful material. And then what to do with this useful material? If the concentration of radionuclides, the dose rates from these materials are below the clearance levels, then you can use these materials unrestricted. No one from a regulatory authority will care. This is under control, of course, but other authorities just to stay safe. But if you exceed the clearance levels, then you need authorization to transfer this use to another user, for example. So the regulatory authority will check, ensure that everything is safe, and then you will get authorization for further use. Or another regulated practice. So maybe the source that was used in one type of measurement will be used in another type of measurements, etc. But if the material is not useful, you don't need it, then it's waste. Then again, you look here now to the clearance levels, and if you are below them, then you treat these materials as normal refuse, effluent. So the regulatory authority from nuclear side will not care, will not interfere, will not check anything, so you are clear. Or you discharge, if this is a gaseous or liquid material, some water, and you are below the clearance levels. Or you need to go to the regulated disposal if you exceed these levels to dedicated repository. So this is a kind of generic schematic, what to do with the nuclear material, a kind of routine. And when you exceed the clearance levels, you are dealing with the radioactive waste management. Radioactive waste management, which here it's a picture of all kinds of activities. Typically, the management is divided into the pre-disposal management and disposal when you dispose of, and then everything goes passive. And in pre-disposal, you have many things here to consider. Some of them are in detail analyzed in our school. So there are here some portions like treatment, that tomorrow I will have a lecture on the treatment of liquid radioactive waste. Yes, and another conditioning on Wednesday about the immobilization of radioactive waste in cements. And so on. Okay, so let's now, as I promised, to look to the sealed radioactive sources. So here it's a photograph of some of such devices. So these are a kind of capsules. In the photograph, these are capsules made of stainless steel, very durable material. Inside of each, there is cesium-137, a very powerful radionuclide by the radiation emitted. And here it's americium, beryllium, and with quite high activities. It's set here 10 curies, and here says 10 to 15 curies. And it's also here emphasized that they are used in many areas of our activities, starting from agriculture, of course in medicine they are used, in industry, in the research, and practically all the countries in the world, they use sources, sealed radioactive sources. So they use the radionuclides which are encapsulated so that there is no any spreading, any contamination around, but there is very intensive radiation coming from these devices. And here it is emphasized that sources contain very high levels of concentrations of radioactivity, large amounts of radionuclides. And the typical content and some sources can be gigabecquerel, petabecquerel. And colleagues, I believe you know what is a becquerel. It's a disintegration per second. And what is a curie, right? You know what the old unit curie, 3.7 multiplied to 10 to 10 power becquerel, then you get curie. So these are very high values, of decays per second. Here it's a table that shows typical utilization use of radionuclides in form of sealed radioactive sources. So you see here cobalt-60, cesium-137. It is decaying via barium-137 metastable, indium, americium, selenium. So these tables can be longer, but I put here this part of the table just to show to you that here the half-life, where these sources are used. So in some irradiators, and here the typical activity, so can be 150,000. The typical radiation that is coming, so this is the average irradiation, 2 levels in mega-electron volts, 2 lines from cobalt-60. In irradiators, in teletherapy, this is a medicine used in industrial radiography to check for some defects in pieces welded or of complex shape. Cesium-137, again, irradiators, medicine teletherapy, in calibrators, iridium industrial radiography to look through the materials, americium well lodging in geological investigations to check what is there inside in the boreholes, etc. Selenium industrial radiography. So here the typical activities in a Curie 4 millions, and then terabecquerels 150,000, and so on for many. So the activities here are very, very high, very, very high. So here it's a photograph of a so-called gamma knife, which is a teletherapeutic device which is used in medicine in order to cut with this knife effectively the tumors. So it is made up of 201 cobalt sources, each has the activity of 30 curies. So it's a huge radioactivity, and because of that, there are 201 lines or rays coming from each source, which are coordinated in one only ray, very powerful, and because of that, it is termed gamma knife. So like a knife, it is focused, it's coordinated, it is directed to the place where the tumor is in a body. And this part, very small part of the body, receive a huge dose of irradiation without damaging surrounding parts, and it acts like a knife. Because of that, it's called gamma knife. So you don't see anything. The rays, gamma photons, enter into the body and do this job, and the patients are saved. The lives are saved by using this device. Other high activity where the activity are huge can be seen in these photographs. So the first one, this one, and this one, they are both actually radioisotope thermoelectric generators. They generate electricity. They transform the energy of radioactive decay into the electrical current, electricity. And because of that, that one on the right side is used in space probes. You know, in cosmic space, now on Mars, we have these vehicles from the United States, from China, and they are powered partly from the sun, but partly from these RTGs, which supply electrical current. And this can be done for years and years, years and years. So you know about the Pioneer, the space probes that now left the solar system. They are hugely far away. There is no any way to capture their any energy of solar radiation. And the only source of power for them is the decay of radionuclides that occur until the full decay of radionuclides. And in this case, it's very often can be strontium-90, plutonium-238, so radionuclides that gradually decay and supply electricity. This one has also huge radioactivities, a very heavy device because it's shielded. Here are a kind of radiators to stay cold, not overheat. And this is used in Arctic areas where it's extremely cold and we need some sources of giving signals to the planes that are flying there. In mountain areas, again, for navigation, they are used. So these are RTG, radioisotope thermoelectric generators. And the device inside, or these are sources, sealed radioactive sources. These are irradiators, maybe that some of you worked with or saw that. So this is blood irradiator. This is self-shielded irradiator, where for research some materials can be irradiated by gamma photons. Inside of these well-shielded devices, there are sources that can be cobalt-60, cesium-137, and others. So partly, Professor Petrov noted to you that the so-called non-fuel cycle waste, it is because of the use of sealed radioactive sources. And here, this is a pacemaker. This is a very small device, and these devices can be even smaller, thin, which the people use in order to stay healthy when they have disruption of the heart beating. So some of the problems with their hearts, and they need a heart pacemaker to give regular signals that will force our heart, the heart of patients, to beat regularly and to stay alive. Because perhaps you heard that some of the people are dying when they are sleeping, because the heart stopped and nobody was, to wake up the person who looked even healthy. And the doctors, the physicians, will give you the recommendation to have a pacemaker. And then you need a source, very reliable, which will continuously, during many tens of years, give you these signals in a safe way, always at the same intervals, in order to stay healthy and to live. So this is the pacemaker, many applications. Other here in the slides shown, so this is a gamma radiography system to check, let's say, the quality of this welding between two pipes, or let's say in oil industry, when you pump the oil through the pipe and you want to check the density of the oil to be sure about the quality of it, you just use such a device, and based on the signal from this detector, you immediately will detect when something is the liquid which is passing in front of the radiation coming from the source is different from usual. So this is radiography system, let's say, or something like that. This one, it's a gauge, americium rubidium source it is used there, which is typically used to check the good quality of paving of the roads, again the density, something like that, the quality, how thick is, how it is maintained, the quality, etc. Maybe it's that some of you saw, maybe not. And this one, all of you should see. This is a smoke detector in buildings, in big rooms, in industrial buildings. The smoke detectors are used to inform immediately if the smoke will appear, a fire hazard. So then the extinguisher will be put in place, and they contain tiny amounts of radionuclides, which also pass through the air. And if in this air some dust, thick dust appear, or smoke, which is very fine dust, very small particles, they will stop the radiation coming to the detector, and the device will immediately signal about the smoke in the room. So these devices, you should maybe so many times, but maybe you are not aware that these are smoke detectors which contain radionuclides. These are sources. So very often the radiation which is emitted from sealed radioactive sources, it is very, very intense and requires shielded containers for their use, for their transportation, for their storage, and particularly important, in particular this is important when you are dealing with the sources that are not anymore needed, so they are termed disused sealed radioactive sources. And these are the covers of an IAEA document, and this is just published by the National Academy of Sciences of the United States of America. So these are two books which are available electronically, you can download for free, which focus on applications and management of these disused sealed radioactive sources, these very dangerous pieces of materials that become waste, and much care should be afforded, much care it's needed in operating with these materials. So if you will open this IAEA document, you will find a table which is called recommended categories for sources used in common practice. And there are 5 categories. Here, categorization on common practices, what kind of sources, and here it is noted the activity ratio. So my intention is to explain a little bit to you this categorization, to emphasize to you that is not used in radioactive waste management. It is not the same. It is not the same as classification of radioactive waste, but is also very important on operational phase, and it's particularly important on interfaces. So what is interface? When an operator, it is bringing to a storage, let's say, facility, or a radioactive waste management facility, the material, including sources, he will use the terms categories of sources. He'll inform you that I brought to you, I transported to you, not brought, of course, I'm transporting to you, I'm transferring to you the source which belongs to the category, let's say 1, 2, 3, 4, 5. There are 5 categories. And the radioactive waste management manager who operates with the classes of radioactive waste can be confused. What is this 1, 2, 3, 5? It is the same as, you know, this high level, intermediate level, low level waste. What is that? How to link them? So one of the purposes of my talk to you, my information to you, is mainly to show where they are and how they communicate with each other. So the IAEA has introduced on international level one of the standards. The cover of this standard that is shown here, it is termed categorization of radioactive sources. And this standard, it is used everywhere now, in all countries. So there are so-called member states. Member states means the states who belong to the International Atomic Energy Agency. They are member states of IAEA. And there are more than 172 or 172 member states. And they all rely in their activities on this system of categorization of radioactive sources. And they are on national level the same. So all of the attendees that are here from many countries, you are from many countries, that is a very relevant information in your country as well. So this system of categorization, it is based, it was developed gradually. In the next lecture, I will explain to you the process of devising and finally publishing these standards based on other documents that are noted here. And finally, explain in this safety guide with this specific number, RSG 1.9. So what is the approach used to the sealed radioactive sources categorization? In introducing the system of categorization of sources, it was used the so-called D value. D, it's from word dangerous. So there is a dangerous dose of radiation coming from the sources, which was calculated and agreed by international experts through the IAEA. So these D values are now well defined, published, explained, and then the system uses the levels around these D values. And actually, there were 5 dose calculations performed by the experts, which accounted for both internal, it means that we drank something, we are breathing, we are eating something, so the radiation will come from inside of our body. An external exposure, it is when we are near the source, we are breathing clear air, drinking clean water, eating the clean but because of external irradiation, they are exposed and we are receiving some dose. So these both scenario, let's say, were accounted, and of course that the most restrictive result is finally accounted. So the calculations are, we say, conservative. We are looking to not exceed this dangerous dose. So what are these dose criteria for the values? So you see here 1, 2, 3, 5. So one, again, I believe that you are already familiar, with these notations. You know what is a grade. If you don't, ask Professor Petrov. He's the head of laboratory of dosimetry in the radiochemistry department. But I believe you should know that. So you see here 1 grade to bone marrow. So I can say so. This is 1 joule per kilogram. But if you don't, but just a reminder, let's say, or 6 grade to the lung from radiation during 2 days, and all the details are given here. Or number 2, so this dose is calculated. 25 grays to the lung from inhaled, low energy transfer radiation, LET means. But now in 1 year, so we were breathing something. 5 gray to the thyroid in 2 days, or source in contact with the body, 25 grays at a depth of 2 centimeters in most part of the body. This is scenario when we put the source in our pocket for 10 hours, or 1 centimeter in the hand for 1 hour. So we kept in our hand, this pencil for this hour, measuring something, playing with it, being not aware what is the source. Or for sources that no way to put them into the pocket, to breathe something from them, etc. 1 gray to the bone marrow in 100 hours. So these are the sources that are inside of big devices, let's say. So these calculations are done. And the next slides, what is 1 gray? It is that much. I believe that I hope that many things you're already familiar with, and Professor Petro explained or is going to explain to you. You have a background and etc. If you look to the basic safety standard recommendations, or to recommendations of a recent document, radiation protection and safety in medical uses of ionizing radiation, again, safety guide of IAEA, you can see here doses over 5 consecutive years, in 1 single year, annual equivalent to E-lens, skin, hands, feet, etc. But look here, for occupational, for professionals, the numbers start for let's say 50, but this is millisievert per year, millisievert per year. And for the public, it is just 1 millisievert per year. Milli, it's 10 to minus 3rd power, 1 millisievert per year. And dear students, I believe also that you know the difference in between the sievert and gray. So they are both are joule per kilogram, but the gray is what the device shows to you, right? You look at the device and it shows the dose rate. The sievert is that one which accounts for what kind of radiation you are dealing with and what organ it is irradiated. Yes, it accounts for the damage to the body. So some coefficients are used but they are the joule per kilogram. So here we are speaking about millisievert per year, and in the previous we spoke about the 1,000 times higher levels of radiations. And now you can look here to this picture that was distributed in Japan after 2011. Most of the people were very much concerned about what's happening because of Fukushima catastrophe. Started to buy everywhere the devices to measure the radiation, to be interested on what are these levels, are they dangerous or not, and etc. And I put here, by arrow, look at what means it, this 1 millisievert per year. It is here. If you look to the natural background, it is much higher, much higher. It's in this specific case in Brazil, but if you'll ask about other places, can be 2.5 average per globe, can be much higher than 10. There are some places in Iran much higher, and the people are healthy there and live. If you are looking to United Kingdom in Cornwall, it is approximately 8, very close to 10. So the background radiation is much higher than this millisievert, but it's still much below, you know, these levels of the grays, which are somewhere here, which are used in calculation. So the danger from sources, it is somewhere here, and it's really very high. So here now you can see these reference doses for the so-called D values used for categorization of sources. So this is a summary of the table of the slide that I explained above to you. This is the summary. And we are speaking about the grays, high doses, not those that we see in normal life. So we are speaking about the danger. And this slide shows to you, for some of radionuclides, what is the activity when you achieve these D dose. So let's say in cobalt, if you have 0.8 QE, then you are at this D dose. And now we can look and understand what is the system of categorization. What is the system of categorization? So there are 5 categories of sources. 1, 2, 3, 4, 5. So this table, it is taken from the safety guide and shows as a function of the ratio of the activity of the source divided to the D level. And the line I edited is not present in this standard, but this is the border. If you look above this line, so the D dose is exceeded from 1 times to 10 times, this is category 3. It is up from 10 times to 1,000 times, this is category 2. And if it is more than 1,000 times, the dose, then the activity is higher, than you are in the category 1. These are really extremely dangerous, category 1. And here below that, they are also dangerous, but not, the degree is much lower. And the explanation will come in the next slides. And the last, they are unlikely to be dangerous, but nevertheless, they are categorized as the category 5. So you see here that it's approximately 100 or even more times lower the activity than this D value, which is already available in form of details in IEA publications and also in the safety guide. So here it's taken from the safety guide, the explanation of the description of the categories. So if you are looking to the category 1, they are described as extremely dangerous to the person. So if some safety measures were not taken, then the danger that can be even lethal can come from the source in few minutes. In few minutes, the dose that the body will receive can exceed the lethal one. So the injuries from these sources is extremely high, and the numbers are presented in the table. The category 2, it is characterized as a very dangerous. In minutes to hours, again, the doses received, the damage received from irradiation from the sources, it's very high and can even cause the fatal consequence to the person. The category 3, which is from 1 to 10 times higher than the dose, in some hours can also cause the damage to the body. Not so high, but the injury can be also very high. So they are dangerous. And then this line, because category 4 and 5, the category 4, it is unlikely to be dangerous. Unlikely doesn't mean that it's not dangerous at all. So if unshielded, is something too long, and etc. will be done with these sources. Also, the damage can occur. In the category 5, it's most unlikely. And this is the case, for example, of smoke detectors. So don't worry about them. It's most unlikely to have any danger if you will not eat them and so on. So this is again, you know, the explanation taken from this there. And here some tables of assigned category for different applications. So you see here this radioisotope thermal generators, extremely high content amount of, these are first category. Radiography, you are second category. These are dangerous. Brachytherapy, it is using medicine to kill the tumors on site, category 2. So they are very dangerous. These for well lodging, moisture gas, category 3, they are still dangerous, Industrial gas as well. And in research, you can move to some weak sources, can be category from 5 up to 5. And other here are also explained. Here is the position of lightning conductors. Particularly these belong to so-called legacy waste. In the past, there were manufactured and used in many countries the lightning conductors. So these were devices which were put on elevated places on high buildings, and because they are ionizing the air around, they are very good lightning conductors. With the tip, and this tip nearby, there is a source of radioactivity. So now they are collected because they can contain even long-lived radionuclides, should be managed safely. You see, they belong from the operational point of view to the category 5. Not much care operationally to receive anything harmful from these devices. But they are of high concern for radioactive waste management operators from the point of view of long-term safety. Because if these long-lived radionuclides like radium will be left in a repository, near surface repository for hundreds of years, this radium can be mobilized from the source and finally achieve the humans and cause harm. So while here they belong to low care, we say category 5, from the radioactive waste manager, they will belong to important level of care. So here it's the place where categorization and management meet each other. And for the management and disposal, we are looking for the hazards during the storage, during the operation, during the transport, but also in the long term, where most important are the radioactivity and half-life, rather than these things which are mostly important from the operational point of view. So we came now to the radioactive waste manager, to the classification of radioactive waste. And this is a cover of another IAEA document standard, safety standard, which is termed General Safety Guide Classification of Radioactive Waste. And this is a schematic of classification scheme, which is recommended now from 2009 by the IAEA to all countries, which doesn't mean that they all are using, but there is a clear trend of moving to use in most of the countries of this schematic. So the classification system of radioactive waste, it's indeed something very much needed as a system, because it gives, in this table it is shown, it provides essential input to the national radioactive waste management policy and strategy. It gives the possibility to have a well-understood terminology, so the all actors, players in the radioactive waste management, which is a very extended first in time. Radioactive waste management is an activity that I started when I was a PhD student. and now I am a retiree. And the same will be with you if you will work in radioactive waste management. This is for entire life and longer. And this also is very extended, not only in time, but also, let's say, in space and so many actors in different parts are involved. You know, generators. Then you need to collect, you need to transport, you need to process, you need to store, you need to dispose of, and so on. So terminology should be well understood. It gives a good broad indication on the hazards. So then we will do appropriate decisions at each step of life cycle, which is extended in time and in space. Provides a systematic foundation for waste segregation by these classes and management programs. Indicates the disposal route for the waste and to develop and employ an efficient management system for operators. So they will clearly understand and do as they should do. For the classification, many approaches were proposed, were used, are still used. You know, it's important the origin, where is generated this waste. It's from nuclear fuel cycle, from a nuclear power plant, let's say, maybe it's from isotope production, maybe from medicine, etc. The physical state, of course, is of primary importance. Is this a liquid, solid, it's gas? Activity concentrations are very, very important. Half-life of radionuclides, then we have short-lived, maybe even very short-lived, long-lived, and so on. Finally, the IAEA came to this publication, this safety guide, in 2009. It was published. And the IAEA classification scheme, it is based on the so-called endpoint. If we are speaking about the waste, the most important is the endpoint where finally the radioactive waste will be disposed of and everything will be passive. So we will not do any activity there. We dispose of, and we cannot say forget, but at least we will be sure that there is no anything that is coming from this disposal site, this disposal facility, and we are sure that it is safe. So endpoint is very important. In the IAEA, the experts that were invited from many countries that worked long time to develop this standard put this classification in terms of two parameters. The one is this one, which is along this axis, horizontal axis, is the half-life of decaying radionuclides. Radioactive waste means they contain radionuclides, which naturally decay. Can decay quicker, or it can take longer time for the decay. So this is along this axis. And here it is written activity content. Activity content is not just concentration. It is a term which covers both of them, concentration and total activity. How much in total do you have, and what is the concentration? Maybe that this total is concentrated in a very small volume, and then it's a little bit another approach. And here you can see that is written deep geological disposal, intermediate depth disposal, near surface disposal, landfill disposal. And in the lower part, it's written exempt waste. This waste, it's the waste which is not interesting for our lecture. If you are below these clearance or exemption levels, then the regulator in your country, from the very beginning, was not asking you to do anything specific, because this is exempt waste. So at least from nuclear part, you don't need to care about this waste. If you are below the exemption levels, then nothing is applied from regulation in concern with nuclear. And only if you are above it, these levels that are specific for each radionuclide and are contained, I'll explain a bit later after the break, in the basic safety standards, etc. So I'll move to this slide, which is a little bit more Obvious. So you see here a scheme. This is the half-life. This is the activity concentration. These are schematically exemption levels. And here there are some lines where from the landfill disposal, you move to near surface disposal, and this is low level waste. Endpoint. Intermediate level waste, intermediate depth disposal. This is intermediate level waste. And then deep geological disposal is for high level waste. This is the line of in between the short-lived and long-lived waste. So we start with it. So you see this scheme, which is recommended by the IAEA to all countries, considers two types of radioactive waste, short-lived and long-lived. And the line is actually 30 years. It is actually the half-life of cesium-137, which is a little bit longer than 30, it's 30.17, but it's still short-lived, so it is here. But if you have something with a half-life a little bit longer than the half-life of cesium, this waste, this radionuclide is long-lived. This is a definition. This is a definition. So long-lived automatically for the people who use the IAEA standards means longer than 30 years. Also here, it is written that short-lived waste does not contain significant levels of radionuclides. This is the half-life greater than 30 years. And there are here some numbers. So what means greater? So typically in many countries, almost arbitrarily, they used the level of 4,000 becquerel per gram in one package for long-lived. Yes, or on average for the entire repository, just 400 becquerel per gram, average for all packages. So some packages can contain much more, but if you take, but not more in each than 4,000. But if you take other packages which do not have anything, on average, you should obtain this number. But there is an explanation here, and we'll come a little bit later. So the plot of IAEA starts with the very short-lived here and very low-level waste. Very short-lived waste is the waste with radionuclides that are quickly decaying. So you can have in the waste some medical typically isotopes, radionuclides, which decay so quickly that no need to care after, let's say, a half of a year or a month, or maybe even during the week, they are gone due to the natural decay. So you store this waste for the decay. We call this storage for decay. And after the natural decay, no more interest to these materials as a nuclear waste. So this is short-lived waste. Very low level waste is the waste which is a little bit above the exemption levels, but not much. It doesn't come to the low level waste yet, but is a little bit above. So we see that not much efforts should be put into managing this waste in order to stay safe. And because of that, they are allowed for landfill disposal. So typically these are slightly contaminated soil, some rubble, with levels of activity concentrations just a little bit higher. And this is specified in national regulations, of course, than exemption levels in each country. And then we move up through the scheme of the IAEA. We are coming to the low-level waste. Here is the waste which requires isolation, containment for periods up to few hundred years. And then, if it's just few hundred years, we can dispose of in engineered near surface facilities, these materials, and how that interrelate 100 years and near surface facilities. Basically from geologists, or let's say generically from the life, we know that during several hundred years, we know how the materials behave. We have a good history of the behavior of the materials, of engineered barriers. We know what's happening on the surface during few hundred years. And because of that, we can make quite confident calculations, so-called predictions, prepare so-called safety analysis reports that prove that it is safe for these materials, which are low-level waste, to be stored in near-surface facilities with suitable engineered barriers. And because of that, this is low-level waste. And you imagine that if we are dealing with the materials that contain long-lived radionuclides in high amounts, they cannot decay during few hundred years, like radium-226. And because of that, they do not belong to low-level waste, typically. They go to another category. So if you move by the content and by half-life, we are getting here to intermediate level waste. Here is the description of this waste. So we cannot rely on near surface facilities, because if we are speaking about the terms exceeding several hundred years, let's say 1,000 years, we see that during 1,000 years, many things happen in the near surface layers. You know, the river change their boundaries, the countries change their borders, and many things change during such times, even an unpredictable way. And because of that, this waste requires a higher level of insulation. We need to go deeper, where the probability of getting into this facility is much lower. So we speak about intermediate depth, not near surface. And here it's a little bit explanation of this number, 4,000 becquerel per gram in each package, or 400 on average. These numbers came from a specific safety analysis report, and then were taken by countries for granted. But they are extremely conservative. In many radionuclides, including carbon-14, chlorine-36, nickel-63, and other, in reality, their concentration can be much higher, can be up to tens of kilobecquerel per gram. So tens of thousands of becquerel per gram without any danger. And this is proved by the safety analysis reports. And in reality, these numbers should be obtained in each particular case, in each country, in each facility, rather than taken for granted from IAEA regulation. This is said in IAEA regulation, that things should be carefully considered. And increasing further the content of radioactivity, we came to the point of high-level waste. So if the content is very high of radioactivity, like in the content of radionuclides spent fuel, or in the waste which is generated during the processing of spent fuel, then this radioactivity, it is so high that even intermediate depths cannot provide the needed level of safety, and we need to very deep disposal, not very, but deep disposal, the so-called deep geological facilities, or geological disposal facilities. Means 300 meters and more, can be 500 meters, can be kilometers, can be even few kilometers. It is where the depth is so high that through the safety analysis report, it is shown that even during millennia, no way for radionuclides to enter into the biological cycles and to do any harm to the future population in the far future on the Earth. In the far future on the Earth. A couple of words about, I have some 10 minutes for this lecture. In 1994, it was the period of safety guide published by the IAEA, which was using a little bit another similar but not exactly the same approach in classification. And many countries have used this previous scheme that was valid before 2009. Now it is not anymore valid. So you can see here the table taken from this previous, published in 1994 guide, which unfortunately contained even a wrong number of 2 kilowatt per cubic meters, which was by mistake somehow published and then even used, but which can cause even the so-called meltdown, as it happened 10 years ago in Fukushima and 30 years ago in Chernobyl. So if the content of radionuclides result in such high concentrations of the heat generators, so the heat power of the heat sources will exceed 2 kilowatt per cubic meters, then the whole body of a reactor will be overheated and will cause the so-called China syndrome. Maybe you don't know what is China syndrome. It was a movie, which in the movie, the artists considered the situation when the reactor is not anymore cooled down. It starts to melt the core, and because of the very high temperature of the core, it starts sinking down. And you know, the people from other countries, from another part of the earth, were worried that this blob of very hot radioactive material will reach them and also kill. So because it came from China in the movie, only in the movie, it is termed China syndrome. But it's just an artistic view of things. And in the current publication, only few watt per cubic meters. It is not 2 kilowatt per cubic meters as the level that is used in country specification, let's say in United Kingdom, in Russian Federation, in Hungary, in other countries. So this was a mistake, a misprint most probably. And for your curiosity, together with my colleagues, Professor Kolektov and Dr. Kashiev, we considered a situation when China syndrome can be used to make such probes made of tungsten inside the core of radioactive cobalt. And because of the very high temperature of this probe, it is able to sink down and to send signals about the composition of the mantle, let's say, or to use for the self-disposal of very radioactive materials, but this is just imagination. Most probably the probes that can signal us about the decomposition of the mantle can be, but this is also a kind of utilization of this China syndrome. So what is that China syndrome? By the way, as a reply to our proposal, it was a cartoon published where you see this funny words here. We plan to bury radioactive waste 13 kilometers underground, but because of the protests from Australia, we had to decrease the depth. So that was a reflection, you know, about this proposal of self-sinking capsules. So I just explained to you about the movie China syndrome. So this is from one of my books that I co-authored. It's in Russian, but I mean, I was in conversation as an expert with the IAEA to play down this number from the publication of IAEA and to be careful with these numbers because it was published by mistake, most probably. So these sealed radioactive sources that I explained in the first part of my publication, they were not covered at all in the previous 1994 IAEA guidance. Currently, in the General Safety Guide published in 2009, the sources are here. So if you look to this schematic, with some numbers that I just explained to you, classification of radioactive waste, high level, and this is exempt, not interesting to us, very short-lived, not much. If we will take some sources, and these are examples, sources. So you see here, sources, this is a cobalt, let's say, source. This is again cobalt source from an irradiator. And we will put this from this table, the sources here. Then you see some of the sources, they are low-level waste, these sources. These use sealed radioactive sources. From the point of view of operation, they are extremely or very dangerous. But from the point of view of an operator of radioactive waste management facility, it's low-level waste. They are allowed to be disposed of in a surface disposal facility, and only some of them will go to intermediate depths, and none of these examples went to the high-level waste sources at all. And I can say you just an additional that in the United States of America, even the RTG, you remember these sources from the cosmic probes, or very, very big sources with a lot of plutonium, strontium inside, shielded, they are disposed of in the Nevada desert in trenches. Because the safety analysis show that there is not much danger in the far future from these sources from the point of view of long-term safety, passive safety. Also operationally, they should be shielded very much, insulated, they are generating a lot of heat. So that's already said. So a couple of slides, I move quickly through. Classification as practiced in countries is not exactly that one which is recommended by the IAEA. But since countries now, due to the so-called joint convention, need annually to report to IAEA the situation with the radioactive waste in their countries. So this is joint convention on the management of radioactive waste and spent fuel. So many countries, not all of them, signed the joint convention. And then it's mandatory to report to the agency what's happening. And then they are forced in their reports to use the IAEA classification, and therefore practically everywhere there is a trend of using IAEA classification scheme. Here a couple of slides that show different schemes, how they applied in different countries. So this is a table about France. This is a table from the United States of America. For they have defense, they have commercial, and it's not the same classification. You see, it's not exactly the same. It's not the same as coming from the IAEA. Russian Federation introduced legally in 2012 a classification scheme, which is a very interesting and scientifically sound one, because in Russian Federation there were introduced the so-called special waste from the very beginning and removal of waste. And the special waste is the waste which is not expedient, let's say, even to touch it now, because the harm from this, it is the legacy waste from former nuclear explosions, radiation incidents, defense programs. So this waste is special waste. And removal waste, where everything is recommended by the IAEA, it is done in the same way. In Russia, you see some details of classification scheme of Russians. A very interesting one is this table. I submitted to Professor Petrov my lecture, so you will be able to have it. This table is very useful because it is a tentative classification. You take the device, you measure the dose rate, and immediately have a tentative classification of, you see, this low level, intermediate, and high level, just based on the dose rate from the waste. And then you will do the measurements and find more exactly what is. This one comes from United Kingdom. For the very low level waste, they introduced low volume and high volume. Something specific and interesting. This is from Finland. This is from Japan. This is from Germany, which actually follows the IAEA recommendations. This is just to show that the same material, which is nuclear fuel component of a nuclear power plant, let's say fuel from a nuclear power plant, depending on the country, will have a different kind of classification. You see, in France, for example, this is intermediate level waste, long lived. In Germany, will be just not heat generating waste. In Japan, transuranic waste, long lived. In the United States, low level waste, but greater than class C. If alpha, then is transuranic waste. So, dear students, conclusions. Categorization relates to safety and security of radioactive sources and is not intended to be applied in waste management. Classification are nationally based, although IAEA has a conceptual scheme devised in 2009 that serves as model, and it is based on activity level and half-life and is focused on likely disposal routes. Some countries continue to base their classification scheme on the simpler 1994 scheme, although there it was a misprint which can be dangerous. So with that, I'm finishing this my lecture, and accordingly to the schedule, we should have a 15 minutes break now.
Yeah, you're right. Thank you very much, Professor Ojuman. Maybe if you have any questions, or after the second lecture.
It's up to the students, but I think they also need a break.
Okay, okay. Just a short question from my side.
Yes.
You showed this classification with short-lived and long-lived radionuclides, where stated that 30 years is the limit between this short-lived and long-lived radionuclides, but cesium is short-lived. So does it state it somehow in documents that cesium is a short-lived radionuclide?
Yes, it is. So
Okay.
in reality, I rounded my numbers. I rounded them.
Okay.
So it's only because of that. Otherwise, the cesium is the border radionuclide, which by definition still belongs to short-lived. Still belongs, and it is specified in the IAEA safety guide.
Okay, because in Russia, in the first redaction of this federal law about radioactive waste management, it was stated the limit of 30 years, but then it was a correction and they moved the border to 31 years, the border.
Yeah. to be consistent with the IAEA and others, yes.
Okay, thank you. So now we have 15, sorry, one more question.
Yes, please, please.
I can ask about strontium-19. What happened? You said that is long-lived.
No, it's short-lived.
Short-lived. Okay.
If I said that, then I'm sorry. I did a mistake, but I can't remember.
Okay, because it's only 28 years. 28 years.
Yeah, exactly. Short-lived,
Okay.
definitely. So no.
I have another questions about technetium and iodine 131. Could we release them into environment, or we must storage?
There are clearance levels, and you must always obey the clearance levels that you have. Well, so colleagues, I don't have the lecture for discharges and so on, but the IAEA has the recommendations and even tables that shows, clearance as discharge is not the same. So for them, you can discharge the iodine, but only within the limits that are approved by your regulatory authority. The IAEA has recommendations through the guidances, but until approval of this in your country, you cannot do. You always should go through the regulatory authority doing that.
Because there is
it depends on the amount of it. Typically, in the cases, if you are from the nuclear industry, then you know that even maybe better than I do. in the cases when some accidents and so on occurred, and some temporary levels are approved and so on. So it's considered case by case. In one of my lecture, I will show you a table with iodine 131, which is for drinking water, but is related to things that happened in Fukushima, just as a kind of demonstration, but is not a reply to your question, sorry.
Okay, thank you. And another question. What is the position of the sources that we import from another country? Should they come back in the country of production?
Yes, the current
or we can storage in another country.
The current position of IAEA through all the meetings and all the documents that are published is recommendation from the very beginning of the contractual agreement to agree on return to supplier. This is the option which agency recommends to everyone. But also it is recognized that the legacy is such that very many sources did not comply with this recommendation. And the agency is encouraging and even helping through national projects, through many other means that the agency can, to arrange for return of the old sources, means legacy, to supplier or to removal of them to organization that then can, have the capability to manage them. But this is done based on new contracts, on new arrangements and so on. So it's a difficult way that requires many years. And by the way, this is the place where the general public interferes and impeded doing that, because the public, when they hear about the returning of a source, they imagine that we are importing radioactive waste in our country. And then the noises and misunderstanding and everything happened on a huge level, and uneducated from this point of view persons make much more harm than good to their population. Where the developed countries like Russian Federation, they have all the capabilities to deal with these issues. And by the way, since I'm working in United Kingdom, on a legal level in United Kingdom, it was approved by the Parliament. It was approved the import of radioactive waste in United Kingdom, and it was passed as legal way of earning money for nuclear industry of United Kingdom. But try to do this in your country.
Okay, thank you.
Thank you very much. And one more question.
Could you please make it more clearly for me on which basis we can classify the radioactive materials on category 1, category 2, category 3, category 4, on the its activity or half-life time, or as you know, the emitted particle from the radioactive isotopes, it maybe have high energy, it have low energy. So on which basis we can classify the radioactive materials?
The basis is the radiation that comes from the material that you are considering. For each material, let's say you are dealing with a certain source, and you know that, let's say, it's cobalt-60. And for cobalt-60, you have got these values. Then you take the table from the IAEA publication, and you look to the number there, and you look and compare with the activity that you have in your material, and you come with the categorization of this source. But this categorization is only for sources. It doesn't have to have anything with the radioactive waste management and high level, low level, intermediate level waste management. This is from the operational point of view of the danger that I try to explain to you. So categorization 1, 2, 4, 3, 5 is for sources, for pencils, for sources of radiation. If you have a container with some radioactive materials, it can be the same radiation like cobalt-60, but this is waste. This is not source. You cannot put it to any category because this is not source. Category is only for these sources, sealed radioactive sources, because once again, they are sealed already. They are the only radiation that comes from there is very dangerous. You can be harmed if you approach it, if you take it out from the shielding and so on. Then you say category 1, 2, 3, 4, 5, and for 1, 2, 3, you keep it always in the shield because they are dangerous. If it is category 5, you can work with this source without the shielding because radiation is not high from there. But that again is not radioactive waste management, is not dealing with the classification as low level, intermediate, and high level. It's okay now?
I'm understanding this only for sources. For sources.
Exactly. Then you are right. Yes, for sources.
Okay. So what I got now from you, we can classify the radioactive source depending on its quantity or the activity.
Not or and. So in the table that you can take from IAEA, you will see for each radionuclide the numbers that gives you the indicative where is this D value. And then you divide your value to D and obtain a number. And if this number is less than 10, you get the category which is 3. If it is less than 100, you get the category which is 2. If it is 1,000 and more, it is category 1.
Okay, thank you. I got it.
Thank you very much. I think now we can go for a short break. Yeah, so let's say in 15 minutes we will be back. Okay. Thank you. Михаил Иванович, мы собираемся. Я думаю, можно потихоньку начинать уже. Большая часть здесь.
So on international regulations, I will start today, but I'll finish tomorrow. So it's divided in two parts, and the regulations can be even added other lectures, because of course there are many standards, many regulations, and they are very often of much practical importance. I will do, of course, my best. Let's first start. Oops. Okay. So I'm starting just with myself. This is brief information about myself. So I'm a member of the International Commission on Glass. And I noted to you that today in the University of Montpellier, the International School on Glass started its work. It's fully online. So the situation in Europe is not certain yet. So we are not allowed to travel easily. So it's difficult, and uncertainty is also here in Europe. So I will give my lecture there online, but not only me. Everybody is there online, including participants. At least you are lucky, you are together, and you also can interact to each other. But of course, be careful, because these new versions of virus are something not good at all. I worked in IAEA for 7.5 years, almost 8 years, in the Department of Nuclear Energy, and with the support of my colleagues, but I was just a leader. We started there the International Predisposal Network. So this is a network of experts who are interested in everything that happens with the waste before the disposal, all kind of processing technologies, also measurement, analytics, and etc. So they are member of IPN, International Predisposal Network. You can join, of course, this network, and you can meet other colleagues there. So yeah. Here it's written other things about me. My focus of interest in science is glass, vitreous forms of matter, and the glasses, you know, are used to immobilize the radioactive waste through the process which is called vitrification. And here it's my books. This one was last month published by Elsevier. So the recommended one is this one, which is an introduction to nuclear waste immobilization. It was the first version developed in 2005 when I worked for Nuclear Technology Education Consortium of United Kingdom before starting to work for the agency, for IAEA. Okay, so let's move now to I wanted just to show to you that I worked for a certain period of time for IAEA. And now I return to academic work. So here it's the content, and before entering into the standards, I would like to go a little bit through the information about the nuclear, and the most by scale area of utilization of nuclear energy is nuclear power. Of course, that we cannot live without nuclear medicine now. This is crucial for diagnoses are based on nuclear medicine. Treatment of many diseases are based on nuclear medicine, application of nuclear energy in medicine. To add here the research and so on. So this is very important, but nuclear power is the massive one which also generates waste. So because of that, it is here. And then I will speak about the IAEA and the safety standards for today. I will finish with the development of safety standards procedure. So, dear colleagues, look here. This is rounded a little bit. It's a little bit rounded. The situation in the world. This is a combined photograph of the Earth as is seen from the space, and you can see the lights because it's illuminated during the night. And actually, these lights show where is the civilization, where is the center of civilization, because where everything is very developed. Then we are working day and night, and during the night, look at Japan. You see how much light it is here, and Europe and Northern America, and here Argentina, Brazil, South Africa, again, very significant. But the situation is such that 2.7 billion people rely on biomass. They are burning, everything which burns in order to heat the food and so on. 1.1 billion people, they do not have access to the energy. 1 billion people, no health care due to energy poverty. Air pollution, many things which call for significant development. And you know that United Nations, the Organization of United Nations, pays much attention to development, everything on the Earth. And it has developed the so-called Sustainable Development Goals, where to focus the attention of civilization, where to put the efforts, to join our efforts in order to make the life decent for everyone on the Earth, not just for the lucky billion and rich countries and so on. So there are many of them, and there are 17 of them. And among them, it's this affordable and clean energy, And by the way, legally, in European Union has approved, you have to heard in the news it is written that the nuclear power has a clean energy, which is reality. Ahead, we have challenges, very significant challenges, because producing energy by other sources than nuclear or renewable, solar, these things, produces greenhouse gases. We are burning fossil fuel, a lot of it, and in a not so long time, to 2050, 80% of electricity will need to be low carbon. And that is why the nuclear now is in a big focus and attention, and a very big one. So it's a big challenge for us. If you look to the life cycle greenhouse gas emission from different electricity sources, then you can see here, yes, hydro is better than nuclear, but even wind is worse. Even solar is worse, life cycle. And then we move to these things that are pumping into the surrounding environment much greenhouse gases, so this is CO2 gram equivalent. But by the way, when we burn the coal and so on, we are also discharging radionuclides into the atmosphere, and we are leaving also the ashes, which contain, transuranic and heavy metals and all kinds of the stuff. So the challenge, it's huge indeed. And because of that, I put here even some quotes of my colleagues. So this is the director of the Department of Nuclear Energy, Mikhail Chudakov. He is original from Russia, Russian Federation. He is now the Deputy Director General of the IAEA and Director of the Department of Nuclear Energy. And he directly stated that nuclear power will have an important role to play. And once the United Nations put these sustainable development goals, everything is done in order to achieve them. And you see that there are conversation and among big powers, big states on the world in order to move together and to join the efforts. Here it's about the nuclear power and the nuclear power development and current status. It is very well under control and reported regularly on regular basis and officially, so reliable data to the IAEA, International Atomic Energy Agency, which IAEA has a system which is Power Reactor Information System, PRIS, and this system accounts for all kinds of activities related to the generation of nuclear power. I can risk and put it, but I will not, spend much time. I mean, the system has a kind of movie that I believe will work. So, okay, until it works, but without stopping too much, it shows how the nuclear power plants were put into operation in different places around the world. And the very first nuclear power plant was put into operation in 1954. It was in the former Soviet Union, and because of that, I put it here separately as a picture. But in this movie that goes, it shows, here it's Russian Federation, the flag, but at that time it was Soviet Union, and then the British, and then the United States, and then France, and then etc. This is the development of nuclear power, of putting into operation nuclear power plants in the world. So that is system PRIS. And this system PRIS, this is a slide taken from the IAEA website. And you can see here what is today. That was on the 1st of July. So a couple of days ago. So we have 444 nuclear power reactors in operation. This is the total capacity installed. 51 more reactors under the construction. This is their capacity. This is reactor years of operation. And here's the distribution of reactors around the world and all kinds of this statistical data, very reliable. You can find in the PRIS system, which is available to anyone. It is open access system that you can enter and check and put in your reports and emphasize and so on. What I want to emphasize myself, look here to the countries. So this is not from the PRIS, but it's so nice to look at. You see here, so the number of operational reactors, it was in 2019, and also it was published. But look here, United States reactors, then France, China, Russia, South Korea, India, etc., Japan here. So by the numbers of reactors, but this is the statistical data which are today in the PRIS system that you can enter there and check. I will not to lose the time. This is also taken from the PRIS. It is to show, so the dark blue, the more intense color, this is reactors that operational, and this is under the construction. And you can see that the most large scale program of construction happens in Asia, in Far East. This is mainly China. This is mainly China, but not only. India also. works a lot. America already has many, but still constructs. Europe, Western, Europe Central, America, Latin, Africa, not much seen to be constructed. And we can look also the situation and the trends through the IAEA, and there are also a movie there. I took just some screenshots. Situation in 2020, 2030 expected, 2040 expected. Look here, United States, yes, North America. It is still North America, but China is already second. At the moment is Europe here, right? Look here, in 2040, the Chinese will lead by the utilization of nuclear power the world. And then Northern America and so on. So very ambitious, very significant growth everywhere, and expanding also in countries which already are using nuclear power. And these are the prospects. So there are more optimistic, there are less optimistic prospects, but it is expected that utilization, use of coal and oil will decline, And renewable, of course, will grow, gas will grow, and nuclear will grow. We expect that. These are prospects, it's not the reality, but it's what do we expect. And all the sources of energy, they are characterized by some risks, inevitable risks, and they produce waste. I already shown to you the CO2, greenhouse gas emissions. But also look here to the death rates from accidents and air pollution, because most of our attention, because mainly of Fukushima, focused to the danger which arises from a pointer option, this one, laser. So this is nuclear energy. So most of our attention is focused, Chernobyl, Fukushima. Nobody dispute these numbers and the magnitude, which is huge. It's real catastrophe and so on. But if you look to the numbers, to the reality, unfortunately, many more people are killed by due to the air pollution and accidents by the other sources. We are forgetting these things. And we also forget that, the other industries which compete with the nuclear, they put a lot in encouraging anti-nuclear movement. They did that very carefully and so on, but without support, nothing happens before, absolutely nothing. Without support, never nothing happened. So because of that, much of attention is to the nuclear, but now it's a clear understanding that we cannot survive and develop sustainable without the nuclear. And you see that at a legal level, things are moving, and the nuclear is now acknowledged as a clean solution of energy. So the risks are everywhere, not only coming from nuclear energy. There is also some danger from the wind, the hydropower, because of the catastrophe and so on. There were many deaths indeed caused. And this is the emission that already noted to you that nuclear, it's generating some CO2 emissions, because we need to produce the fuel, to transport it. So it's not just nuclear reactions occur in the reactor. So risks. If you look to the waste from electric power generation, and shall be normalized, of course, and here it's 1 gigawatt per year, so one nuclear power plant will work 1 year. Then if you look to the generation from the gas and burning, and from the coal burning, we are speaking about tens of millions of tons. Here also millions of tons, and here, in order to see on this plot, we need to use another scale, because yes, we have some tons of fuel, some 100 tons of solid and liquid radioactive waste. So we are speaking about some 100 tons of the waste generated by the nuclear. Because of that, it was recognized as a clean source of energy. So the situation with the nuclear energy is that it has a potential exceeding value of the role that is playing and is going to play in securing electricity supply, and does that safely, can do that safely. If it is integrated, it's not the question of replacing other sources by nuclear. It's to add and to move gradually, replacing the less safe by better sources. By the way, this plot that shows here the globe shows where in each countries we do use nuclear power plants, and blue we use research reactors, and this one is just, I noted in the previous lecture, what is these used sealed radioactive sources. So the globe is covered everywhere the sources are used. So the point is also that we need to build the trust in the public and to demonstrate that we are able and we are doing safely operating and safely commissioning of nuclear power plants, and we safely manage the radioactive. We also say nuclear waste, the same. So how it is done, this approaching, managing safely the radioactive waste and everything which is done in the nuclear industry, nuclear sector. This is the most influential organizations which provide recommendations on radiation protection. So IAEA, International Atomic Energy Agency, then there is a United Nations Scientific Committee on the Effects of Atomic Radiation. Then there is a very important International Commission on Radiation Units and Measurements, which gives recommendations how to develop the standards and so on. And the International Commission on Radiological Protection, this one. So the IAEA develops its standard based on the just noted to you, like ICRP publications, recommendations. And the IAEA is the world's center for cooperation in the nuclear field, and it seeks to promote safe, secure, and peaceful use of nuclear technology. Only peaceful use. Only peaceful use. Because things, how they develop it. So a little bit you recall from the school, from your university years, that X-rays were discovered by Röntgen long time ago. So the photograph of the hand of his wife with the ring here. Then in 1896, Henri Becquerel discovered the natural radioactivity. And you see here a barrel with so-called radium water, and here a needle. In this case is what they just show. These are peaceful use of the newly discovered nuclear things. Newly discovered X-rays that penetrate through the body and leave shadows that shows about information about the content inside of the body. You don't need any body cotton to look what is there inside. You can see from outside a broken bone and many others. So it's the use in medicine, peaceful use. Initially, it was discovered that the radiation has a very good action on the health of the people when applied to low levels. And even the radium water, unfortunately, was, initially without good understanding, sold, used, radium baths and many radium treatment. Later they were prohibited, and of course they are not used anymore. But that was a part of the history. But radium needles, these are needles which contain inside certain amounts of radium-226 radionuclide that if put in contact with a tumor in a body, it is killing the tumor there. So if this needle is inserted into the tumor, it saves lives. It is a way to be used in medicine. 1934, the Curies have discovered the artificial radioactivity. And again, here I just put that, these radiations and radionuclides and so on, there are many, many peaceful uses. But then it was discovered the fission. Then it was realized that the amount of energy which is released in the nuclear reactions, in the nuclear fission reactions that can be done at a large intensity in a self-developing, self-sustaining chain reaction. So many reactions can occur together and release so much energy that can be weapons. Very much energy can be released. And the project appeared. So here is the Manhattan Project, because it was still the Second World War. It was the fear that this bomb will be developed at the enemies. And the Manhattan Project was initiated in the United States. Here is the map of states with the sites involved in the Manhattan Project. Only a very rich and powerful state was able to put into operation. Very powerful state with many resources, and they started in 1942 with these research reactors in Chicago, in the city. It was just a half of what energy released in the reactor, but it has shown that everything it is indeed manageable. But it was also realized during the operation of these reactors that they were developed to generate plutonium for bombs. And along with the plutonium, so much energy was generated in these reactors that it was necessary to, they could lead to this China syndrome that I just explained to you. So it was necessary to evacuate this heat from the inside. And in addition to the military use, so here is the slide that shows, the first plutonium bomb that was due to the transmutations that occurred in these production reactors developed in Hanford. The first explosion, Trinity in States, and then with enriched uranium and plutonium in Japan. But in parallel to that, because it was realized that very much energy is generated, the reactors for peaceful use started to be developed. And already I noted to you in the press, the first power station, just 5 megawatt, and then 10 times more in Calder Hall in the United Kingdom, and then 60 in 58 in the United States, in Shippingport. And then the history of utilization of nuclear power started, and the press shows how that was done. And it was a clear move from the military purposes and uses to the peaceful. And the President of the United States, Eisenhower, played a significant role. So he, in the United Nations, proposed and was the leader, took the leadership of developing an international organization to take care of the use of nuclear power only for peaceful uses, because it was understood very well that the danger for nuclear explosions, it is so high, so huge, that can lead to the end of civilization and destroy the life on the earth. So his talk in 1953 with the proposal was at the United Nations, with the quote from him. And in 1957, officially, the International Atomic Energy Agency was launched as an organization to take care. In 2017, I was a member of IAEA. I was working for IAEA, sitting in an office in Vienna. At that time, the general director of IAEA was Yukio Amano. He was the general director during 10 years, from 2009 to 2019. He passed away, colleagues, in 2019. And this is a quote from him. He proposed to change the logo of the IAEA. In the past, the logo was Atoms for Peace. And now the logo of IAEA is Atoms for Peace and Development. Atoms for Peace and Development. So nuclear energy, health for development, and this is, let's say, the stream of the work of the IAEA. The current general director of the IAEA, general director of IAEA is Rafael Grossi. He is from Argentina. He came from Argentina, quite young by age. I had the honor to work with him because during my term for IAEA, I was the technical officer for the projects on nuclear waste management in Argentina from the side of IAEA. So I met him many times in meetings, etc. when he was the leader of Argentina. Let's say I never worked with him personally, but I know him, and he is very active person and leads the IAEA in a decent and interesting way, as did Ikio Amano, with whom I worked for almost 8 years. So after 60 years of work, here is the exact number. So the IAEA has now 172 states that are member states, belong to the IAEA. The staff is, this is a rounded number, 2,500 people from 100 countries. The headquarter of IAEA, it's in Vienna, but in Seidersdorf there are laboratories of IAEA. In Monaco there is a laboratory which works on the seas, marine laboratory. There are regional offices in Toronto, Tokyo, liaisons officer in New York and Geneva, and formally IAEA is an autonomous international organization, but is within the United Nations system. So because of that, it reports to the United Nations General Assembly and Scientific Council as needed, Security Council. Partners is with many organizations, so not of the IAEA, of United Nations. So the main areas of work of the IAEA are in area of safeguards and verification. It is where the peaceful use of nuclear energy is ensured. So to prevent the further spread of nuclear weapons. Therefore, there are the division, a department of the agency is dealing with the inspections. So they are checking the content of fissile materials and so on around the world. The next area is the safety and security. It is where the IAEA works to protect people and the environment from harmful radiation exposure. It is where the safety standards are developed and then are recommended to be used, and they are used in member states. And the area of science and technology, where the best practices are taken from countries and through the IAEA are also spread and are given, offered to other countries through the experts, through also facilities, through all kinds of the support. So here it's written, they develop standards and guidance, they provide review and services, they help to support capacity buildings, they develop networks. So one of them is IPN, International Predisposal Network. And of course, the agency is providing a forum for communication, increases the transparency, so shares the lessons learned, organize many workshops, conferences, and so on. Just last week, I noted to you, I participated the whole week in an IAEA workshop with the countries from Europe that looked on decommissioning radioactive waste. How to deal with the waste which arise during the decommissioning of different nuclear facilities. So the agency has like 3 pillars of the work: safeguards and verification, safety and security, and science and technology. So my work for agency was in this part of the pillar. Because if you look to the departments of the IAEA, so the IAEA has 5 departments. Nuclear applications, here is the science mainly, the scientific research, for example, the fusion, utilization of fusion to generate electricity, but not only, different nuclear reactions and so on, databases and so on, all kind, use of nuclear energy in medicine and so on. This is this department, nuclear applications. There are many applications in geology, in many areas. Nuclear energy, Department of Nuclear Energy is the department I was a member of, because I dealt here with the management of radioactive waste. Safety and security is the department which develops the safety standards. Safeguards, it is where they do these inspections and ensure that there is no the non-peaceful use of nuclear energy anywhere. And the largest, the richest, the most powerful department is the Department of Technical Cooperation. If some of you in this room dealt with the IAEA, most probably that was via the Department of Technical Cooperation, because they have they help the countries, they have national projects, they have the funds, they organize the workshops, the conferences, and many other things. So most of the activities are through the technical cooperation. Not only, of course, but it's just the largest by the possibilities and the things that they are doing. So the statute of the IAEA authorizes the agency to establish safety standards, which aim to protect health and minimize danger to life and property. And these standards, the IAEA must use in its own operation. So everything that IAEA through technical cooperation from any other kind of arrangements, etc., does, it is following the standards. The standards of the agency are like law for the members of the agency, for any project through the agency, any activity through the agency. So this is something that must, no way, you must follow these standards, which is not the case for you, dear students. You came from countries and you are regulated by your national laws and regulations. And the documents that are coming from the agency are just recommendations from you. They are not mandatory. There are few exceptions, of course, because, for example, transport regulation. If this is international transport, no way. So transport regulation is international. There is also this joint convention. If you signed it, this is a law. So then you must follow it. So there are some exceptions, but otherwise, the standards, including those that I will describe to you, these are recommendations from me. But the countries are typically using them as the basis, and most of the national regulations are, if not repeating them, almost repeating them. So they follow these recommendations because it's a big chunk of work already done. No reason, to do and again to derive figures and approaches when everything is already there. So let's now move to the nuclear or radioactive waste. It says nuclear waste because the radiation comes from nucleus. So both terms are correct. Radioactive, it means that we are dealing with these radiations. So the materials are radioactive. So here is the definition. Again, it was shown that is taken from the basic safety standard. And again, here I'm emphasizing to you that this definition is for regulatory purposes. Because if you look around, then practically everything is radioactive. Even we, with you, I, everyone, we contain some radioactive elements. We contain carbon-14, no way. We contain some tritium a little bit, and many other radionuclides we contain, because everything around us is a little bit radioactive. Because the life is radioactive a little bit. So there are some levels, and even if these levels are exceeded, we know these levels, then these materials and this waste is radioactive. If not, is non-radioactive. Although, if you are technically educated, you understand that that doesn't mean there is nothing radioactive there. There is some radioactivity, most probably. Absolutely clean without any radioactivity materials, of course, can be produced and exist. And for example, the fossil fuel that we are digging from underground that are burning the nuclear power plants does not contain carbon-40. And it was a time when after the Industrial Revolution, by the way, the content of carbon-14 on the Earth started to decline because, you know, everything that was burned was pumping CO2 into the atmosphere without carbon-40. And who knows what this good or not. Okay, so if we are dealing with radioactive waste, then we have the radioactive waste management. And this is a collection of many activities. So we have to deal with the radioactive waste from nuclear applications, and this can be medicine. Professor Petrov explained to you the sources of radioactive waste. So nuclear facility operations, decommissioning of nuclear facilities, environmental remediation, these yield radioactive sources. And then we enter here into the predisposal, and if you'll successfully pass through the predisposal, we will move to the disposal. And in predisposal, there are many things to do. We need to characterize, to sort, segregate, reduce the size if it is big, decontaminate, treat, immobilize, pack, use the packaging, store, and then maybe we will get to this point because in many countries, a lot of radioactive waste is just pending disposal, and it takes a long time to get to the disposal, particularly for higher level radioactive waste. So here is the whole story. It can be discussed for a long time, but you see here generation, and then you enter into this predisposal management with the treatment, conditioning, interim storage, transport, disposal. Here it's a good place because due to the decay of radionuclides, the radioactive waste have the option, because of the decay, to go to the disposal, and sometimes that can be just simply disposal because no more radioactivity there. So when we manage the radioactive waste, we must use safety standards. You in your country, if you will enter into this business, you must use your national regulations. I work for the agency and I must use IAEA standards. IAEA standards anyway are the basis in national regulations and therefore are useful to anyone, and at least explain to you what are the basis of standards that you are forced to use in your countries. And maybe you got something missing. And then if you are again involved in this business, it will be useful to take some IAEA recommendations and to adapt to your country, to your maybe not country institution, to your city, to your place where you work, to objects that you are responsible for, and etc. And to use them your local regulation in order to act safely. So safety standards, they regulate the nuclear radiation safety, but this is a national responsibility. National responsibility. So I explained to you, many countries, they decided to adopt IAEA safety standards for use in their regulation, or at least to use them as a basis, And in 2006, the IAEA has published a unified set of principles representing common safety philosophy across all areas of applications of IAEA safety standards. The name of this standard, it is called Fundamental Safety Principles or Safety Fundamentals, SF1, published in 2006. This is the cover. So this SF1 document, IAEA standard, superseded the previous safety fundamentals publications that were issued before, and it was published in 2006. that regulated the safety of nuclear installations. That was 1993 document. You see the series. Principles of radioactive waste management, 1995. And third document, radiation protection and the safety of radiation sources. So instead of using these documents, the safety fundamentals combine them together into concise principles that, if followed, ensure the safety of utilization of nuclear energy. So this was recommended by the statute. It was a request of the statute of the IAEA. You see here, to establish or adopt in consultation and collaboration with competent organs of the United Nations. Because of that, the organization I noted to you, like ICRP, International Commission on Radiation Protection, with the specialized agency concerned, standard of safety for protection of health and minimization of danger to life and property. So agency started to work in developing standards long time ago. So that the very first one was in 1958. You remember organization of agency 57. Next year, it published safety series #1, safe handling of radioisotopes. It was so long time ago, so long time ago. Understanding everything was different from today. But this standard started to be used and provided actually quite correctly the recommendations and means of doing everything safely. But through these many years, so many other publications arised from the activities of the agency. Here, some 230 have been issued by the safety series, too many of them. So even for the basic, you see here 58, the very first one, then regulations for the safe transport of radioactive material, 61, and then the first DSS, 1962, and many other kinds of documents related to different activities were published by the agency. So it was an attempt to publish safety series in the agency, and they put, you know, here safety fundamentals, safety standards, safety guides, safety reports, and safety practices. It was an attempt to do the safety documents in such a way. And publications are in place to do this kind of systematization of IA publications. So they were different by color and so on, but altogether that resulted in these 230 publications, so many of them. So because of that, the efforts were put in place. The experts worked for long time, experts from organizations, experts from different countries, leading countries that know the business of working in the nuclear energy area. So here's the definition of the safety. But here it's just to show that the main documents, is 3 were merged into just one, published in 2006, which is the fundamental safety principles, fundamental safety principles. So today, the safety fundamentals is the top document, and other documents under it, following its logic, are developed. So here, if you go down in this picture, you have more and more publications and documents. So here, a reasonable number of them under the safety fundamentals. So in this part, general safety requirements. What are the requirements to governmental and regulatory organization framework? What is the leadership and management for safety? What is the radiation protection and safety of radiation sources? What is the safety assessment? So these are general safety requirements. So the requirements concisely are put in these documents, and there are already many, 7 volumes. And then specific things. For example, how to evaluate for a nuclear installation a site. And there are specific safety requirements. How to ensure the safety of nuclear power plants. Again, is the specific safety requirement. how to design and construct, how to commission and operate a nuclear power plant. Here, so it's divided into two parts. Safety of research reactors, separate document, separate specific requirements. Safety of nuclear fuel cycle facilities, producing, for example, the nuclear fuel. Radioactive waste disposal facilities of this repository. Safe transport of radioactive materials. So these specific requirements are even international, because no way to avoid them, because you need to cross the borders. So there are already many of them, but there is a logic construction, logic distribution of safety documents, documents at that resembles a form of pyramid. And then under these documents, there is a collection of safety guides. There are many that, focuses on different areas. And under this, there is a collection of technical documents, which are actually describing the practices in different countries. So if to say about my work and my contribution, I participated in developing many of technical documents, more than 20. I am listed as a co-author of them, so I was invited along with many other experts, so I contributed in developing these technical documents. And one or two only at the level of safety guidances. And for these documents and so on, I will explain you that there are special commissions and so on that are responsible and do the job to properly develop and approve these documents. So on the IAEA website, if you go there and look there, you can find, this is the view from there. And if you search for safety standards, you can find all of them. You see, these are just things that I explained to you in these general safety requirements, general safety requirements. This is the BSS part 3. BSS in the past was named because of that. It is still called by the older people like me, basic safety standard, but it's basic indeed. So you can go further and you see here general safety requirements and so on. So all of them are listed here. And this is the link that I will not press on, but that you can do that and get there easily. So this is how now the documents are organized in the International Atomic Energy Agency. On the top, there is safety fundamentals document. Then there are general safety requirements, and then these are split in specific safety requirements. Then you got general safety guides, specific safety guides, and then under this pyramid, many technical documents that show practices, how it is done in this or in this country, and what is important here and why all of them are needed. If you go to this document, there are generic statements. And to go to the real application, you need much more details. And most of the details are here. Most of the details, but they are already so specified, going to the activity, concentration, and everything very exact in the figure that you cannot use in your documents. So all range of documents are needed if you are going to develop and to use something in your country. So how the standards are developed? Here is the schematic. Everything starts with planning. So depending on the demand, on the real need here and there, the kind of work plan is developed, is outlined. It can be done by an IAEA member staff or by the several members of IAEA jointly with some experts from the countries and so on. They prepare draft preparation profile, proposal, which is then prepared by the Secretariat, and it is directed for the review by the Safety Standards Committee and the Commission on Safety Standards, which decide whether it is a real need to develop it, and maybe something is missed, and where is the place among other standards of the agency, and so on. So looks on in harmony and professionally to keep together organized in the agency for the standard which is proposed, identify whether it is needed or not. And then, depending on the area where this standard is, there are safety standards committees in the agency, which are standing bodies of senior experts, so very experienced experts. So the most important senior means experience. The mandate is for 3 years, and they advise the Deputy Director General on the overall program for the development, review, and revision of standards. Because in addition to the standards, new standards that appear and are proposed, the older standards, their term is typically 5 years, and they are reviewed as kept as they are, but very often they are a little bit amended, a little bit changed, sometimes even more, particularly when something happened like Fukushima. So then the standards are reviewed, getting into many details to look at what was wrong. Maybe something is wrong with standard. So it's very important work. So these committees, they advise the DDG how to work and then move forward. And there are committees on Nuclear Safety Standards Committee, Radioactive Safety Standard Committee, Transport Safety Standard Committee, and Waste Safety Standards Committee. So this group of us, so they are coming from member states, from the countries. It's a serious organization that gives then the advices to the DDG, Deputy General Director, and also they review and approve and draft safety standards that are already under the war, these committees. And then the Commission on Safety Standards, it's the standing body of senior government officials. So they are coming from the ministries, from, let's say, Rosatom, DOE, and so on. Mandate for 4 years. And they have the role of overview with regard to the safety standards. And their advice goes directly to the Director General on the overall program of regulatory aspects of safety. They also are looking and checking coherence and consistency between the safety standards. Issues appear by the committees and endorse draft safety standards that are approved by the committees. So the work, it's a long-lasting, taking many efforts, many persons and organizations. It also has interaction with them all 172 member states that can request change in the safety standards, because the standards are very important. From one side, they should regulate the activities to ensure safety. But colleagues, it is everywhere in our life a balance on things that we want and we can. And we can impede the development. We can stop the development of something, which if we will put something in a standard that we not allow utilization of this on this. And we are actually using this Alara principle as low as reasonable, achievable. We should use the common sense and reasons everywhere. Assess the risks. We cannot exclude all the risks that exist around us. So sometimes in the standards that are coming from the IAEA, you don't see exact numbers. You can see some generic statements and so on. It's because that could not be done, because one state proposed to use a certain number as the level, and another said no, I will not approve this one. I should use 10 times more, or I insist on 10 times less, and so on. So there is a conversation. I'm giving just you an example of how things have happened. So that's a kind of compromise, let's say. And the standards are standards. These are not just words, but in some places they use the language which allows a kind of flexibility. And then is the place where you, other people from member states, from the countries, can put, if they like, their numbers and use them. That is affordable and useful for the practices. So it's a long way from here to publication. So I'm closer to the end. So just to show you an example. So I was, let's say, you see here, it's my family name. I was working at that time in Scientific and Industrial Association Radon, Russia. So this is a safety guide for predisposal management of radioactive waste from use of radioactive materials, medicine, industry, agriculture, research, and education. SSG 45. It was published in 2019. So 1.5 years ago, 2 years ago, it was published. But colleagues, we developed this standard in 1999, 20 years ago. This is me. If I'll show you, if you look to the screen and see my image here, you see here, not much hair on my head. I was young, full of energy and so on. It was in 1999. Some of the people here are not anymore, they passed away, not some, but one. Okay, Vladimir Tsiplenkov, he was a member, staff member of agency. He invited me from Russian Federation to be an expert when he was developing this standard, but came to publication only after 20 years. Two decades it took to put this standard, this document on the paper, and now it's a document that must be followed by everyone from the agency, by every active project with the agency, and is highly recommended to all of member states, countries in the world of the agency. So to go now to finishing, the organization of the safety standards, say the documents in the agency is like a pyramid. On the very top is the safety fundamentals, principles, safety principles. And then there are safety requirements. And these documents in dark red color, they use the language shall. So you know, shall is not must. So you will not be punished and put into the jail if you will not follow, but you shall. You shall. It's almost must. You know, in English language has different order of what you have to do. So if you say you have to do, you have, but maybe you will not do. But if you must, no way to avoid. You must. If shall, it's almost must. So you are not obliged, but you must do it. Do it. Then you go to the safety guides, and here the language used in these documents, it is should. You know, it is good to do it. This is the understanding. It is good to do it. Do it if you can. You can, you know, translate in other languages, you know, these modes of using must, shall, should, and so on. So then you go to the technical documents. They are not using at all. Do as you consider necessary to do. Here it is explained how we did it. How we did it in this project, and this project, and this project. And we follow the standards, of course, because the agency, before publishing any document, does the review, and that also takes time. And this is explanation why agency is publishing the documents at a very slow pace. It takes long time to get anything published in the agency, very long time. So let's say I publish 10 books through Elsevier, from other publications. It's hard to do it. It's a big work. But only as a member of agency, only 5 documents as a scientific secretary, I was able to put them and to distribute to the countries, and submitted a couple, but not published during this my term in the agency. It's a difficult work. So here is the conclusion that the agency is required by the statute to promote international cooperation along all the regulating safety is a national responsibility. Radiation risks maybe transcend national borders, and international cooperation serves to promote and enhance safety globally. And international cooperation is facilitated by international safety related convention, codes of conduct, and safety standards. And the IAEA safety standards are applied by the IAEA to their own operation and are recommended for the use by states, national authorities, and by other international organizations. So, dear students, again, thank you for your, you know, careful listening, because I see the room in front of me. I put here, in addition to the thank of you, we are publishing this special issue of the Journal of Sustainability dedicated to nuclear waste management and sustainability. So through it, and here is a link that if you push on it, you'll get to the page of this special issue. So now I really finished. So Professor Petrov, I think if he is in the room,
yeah.
The floor
Thank
is
you very much. Thank you very much. Do you have any questions on tech docs, on regulations? Yep.
Hello, thank you for the presentation. My question is regarding to safety, nuclear safety and responsibilities. You already mentioned that nuclear safety is the responsibility of the national, is a national responsibility. But when we consider the previous accidents in Fukushima, in Chernobyl, we can see that the impacts, the accidents are more affecting the other countries as well. So is there any plan for the future that this responsibility can be monitored by the International Atomic Energy Agency? I mean, should be some rules that the states must obey these rules. Shortly, my question is, we can change from should to must.
Yeah. Thank you for using the word that I emphasized. Yes, the answer to your question is yes. And the instrument, it is the so-called joint convention. So the countries, the states that signed the joint convention, they are obliged, and because of that, they must, so the word is not must, this is shall, report everything. They are controlled by the IAEA. They report to the IAEA. The IAEA, of course, is helping them to manage. So because of that, there were reports on Chernobyl. There were reports on Fukushima, and everything was controlled and reported to everyone on global level in a responsible manner by the IAEA. So all the data were checked. They first were reported, inspected, and so on by the IAEA. So the instrument, it is joint convention on radioactive waste management and nuclear fuel management. Joint convention, this is the name of document, and this is binding document. If the standards that I explained to you are recommended, the joint convention, if you sign it, then you are obliged. This is an international convention that you must follow. The wording is shall, is not must, but if you'll open, then you'll find all the statements and so on. The name is joint convention.
Okay, thank you.
Any more questions?
You know, even if you may have a small question and so on, leave it for tomorrow, because I did not finish with the standards. So don't take things that tomorrow will be maybe explained in more details.
Yeah, okay. Thank you very much. So now we have a small coffee break again. So thank you.
Then I'll see you tomorrow.
See you tomorrow. Yeah. Thank you. And just a short technical note again. So after coffee break, I would propose that we will have a group photo just in the front of the building. After coffee break, everybody will happy. more relaxed, and yeah, everybody will smile and the photo will be better. And after that, we will have short, let's say, presentations, just few words about you, just one by one. And after that, we will finish for today with formal part. And then I think that at 7, they will wait us at Durdin restaurant, and we will go there. Okay, so after finishing the formal part. Okay. At 7, not the conference, not the hotel, but another place, Durdin restaurant. If somebody are not going to go there, please inform me that we know how many people exactly will be there. Okay. Okay. So now coffee break. So now we will continue with just a short presentations of the participants. I would propose that we will go just one by one. You will say your name, and as far as it is not always really good to hear the name by hearing, by sound. I will just mark the name on the slide. Yeah, okay. So I propose to go from this side. Just your name, your current position, your university or organization, and what is your field of expertise. Okay.
Okay. My name is Dr. Girma Kabatu. I am from Ethiopia. I work for the University of Bahir Dar. I did inorganic chemistry, particularly. I just want to extend my career into nuclear and radiochemistry. I think that's enough.
Hello, my name is Ines, and I'm from Egypt. Now I'm a master student at my final stage, so please wish me luck. Actually, I'm interested in waste management as it's working.
Because microphone is only translating your voice online. It's not like your voice
Okay, my name is Ines, and I am from Egypt. Now I am a master student at my final stage. So wish me luck. I consider myself as a person that's interested in environment and how keep it safe. So waste management is my perfect field. Actually, after my graduation, I was a part of a project that's interested in improvement the cement with nanomaterial to be as a good matter for radioactive waste disposal. But because of financial issues, it was stopped. So when I was accepted in this school, I think it's like a restarting step to this field again, and will guide me to be choose a good steps in my next career. Thank you.
Hello everyone. I am Ahmed Ismail Al-Hazaka. I am from Egypt. I finished my college in Egypt, and I got my master degree also in Egypt. After I finished the college, I joined to work in a company, oil and gas company. I worked there for 5 years. After that, I joined the work in university. It was I just my father wanted that to go to the university to work there. Of course, I graduated with excellent. I was the second in my year, but that's all. I just finished when I just finished my master degree in Egypt. I looked forward to start a PhD degree outside Egypt. I found the first chance was in Russia, and now I almost finished my PhD degree in MIFI in Moscow here. Thank you. Ahmed Baslidny.
Hello, my name is Cüneyt Kahraman. I'm from Turkey. I'm a mechanical engineer, but then in my master, I started working in nuclear applications. Now in my PhD, I'm also working on nuclear energy. And I'm working as research and teaching assistant in another university in Turkey. Thank you. It's Junaid Kashima. Just one up. Yeah, that one. I have two names.
Yeah, Kamal Kayode Abdurrahim. But there's a mistake in my name. Kayode is Kayode, not Kayide. Kamal, Nigeria. Kamal Kayode. Okay. All right. Now.
Okay.
I had my first degree in Nigeria in electrical engineering. Then after then, I got employed with Nigeria Atomic Energy Commission. Then I had my master's in nuclear engineering. After then, I went to the UK for another master's in advanced control and system engineering. After then, I found myself here in Russia. I've studied Russian language from scratch. Now, I'm in MIFI studying electrodynamics and control.
I am Muhammad Mustafa Al-Saeed Mustafa Atta from Egypt. I am researcher at Egyptian Atomic Energy Authority. My research area is radiation processing of materials and fabrication by ionizing radiation. My PhD was in fabrication of reduced graphene oxide by gamma radiation and comparing it with chemical methods for supercapacitor applications. Current projects contain fabrication of flexible supercapacitors by graphene and graphene composite by ionizing radiation.
Hello, I am Muhammad Omar from Egypt. I am studying engineering of nuclear power plant design and operation. I studied in Egypt 3 years and complete here in Tomsk Polytechnic University. Now I am under graduation. Thank you.
My name is Ahmed Shahin. I'm study nuclear power plant design and operation, specialist degree. I'm studied 3 years in Egypt and complete in TBO, Tomsk Polytechnic University. второй.
Hello everyone, my name is Hisham Mohammed. I am Egyptian PhD student in Oral Federal University in Ekaterinburg. I got my master degree in Al Azhar University in Egypt, and then I got a scholarship to complete my PhD thesis in Oral Federal. My PhD topic it's interested to dosimetric the radiation dose to human after treatment by radiopharmaceuticals material like technetium, zirconium, or technetium, zirconium, and lutetium. Actually, I almost finished my PhD thesis, and I think this is the last year for it, and I hope defense in it in Moscow State University here. I hope it. Okay. The council which we need to discuss to defense here in Moscow State University, because actually in Ural Federal University we haven't a specialist in radiation biology or medical physics. So we yes, more related, yes, of course, yeah. Yes, radiobiology and yes. Oh, thank you.
Hello everyone, my name is Muhammad Hanafi. I am working in at Nuclear Materials Authority in Egypt, and now I am a PhD student in Oral Federal University in Ekaterinburg, Russia, and I got master degree from Egypt, and I came Russia in 2016 years, and now I actually I am finished the PhD, and also we need to solve the problem of council to defense the PhD dissertation. So we can discuss with director of chemical department to find the suitable council to finish the PhD dissertation. My dissertation talked about the detection of radionuclides in the urban environment, like residential areas on small scales in green size fractions. Thank you very much. Yes, me получили отлично, no exams, few exams. Thank you.
Hi everyone, my name is Dr. Ahmed Khayb Ali Sak. I am a researcher at Egyptian Nuclear Materials Authority. I had a PhD in radiochemistry. My major field is environmental chemistry and radioactive waste management. I taught in organic and analytical chemistry at University of Hull in the UK before. Also, I had a postdoc at the University of Central Florida in environmental chemistry in America last year. Thank you, everyone.
Hello, my name is Zarub Alexander from Belarus. I research staff in the Joint Institute of Nuclear and Power Research, and my scientific field in specialization radionuclides in water solution.
Good afternoon, dear colleagues. My name is Katerina Venglinskaya, or simply Katya. I'm from Belarus. I'm from the same laboratory as Alexander Zaruba. I'm the second year PhD student in that institution and junior researcher at the same laboratory. And my PhD thesis is about sorption and desorption of cesium-137, strontium the 90s and the 85s and cobalt the 60s. And that's all. Thank you.
Hello guys, I am Om Niranjan Misra from India. I was working in Indian Space Research Organization early 2004 to 2007. At the time, I was in charge of nuclear power plant monitoring and nuclear waste monitoring in India by help of space technology. So being a geophysicist at that time and working as a mining responsible activities, I was dealing with nuclear waste, nuclear power plants, and natural catastrophes. So since that time, I was interested with nuclear wastes and nuclear waste safe deposits. But since 2006 and 2007, I have moved to Germany, then Italy, Japan. So more than 13-14 years in Europe. I changed my whole career towards satellite, from satellite application to satellite technology, then satellite space propulsion and human space flight. Presently, I'm doing my second PhD work in MEFI. Well, my PhD work has nothing to do with this school, but this school dragged my attention because I want to update and enhance my so long time existing understanding about nuclear waste, especially the present trend technology about safe deposit and nuclear waste management. So I am keen to see what are the latest developments in this field of nuclear waste, which is a biggest headache to every nuclear possessing countries. Fortunately, being hailed from India, India has 21 nuclear reactors, so it is really a matter of concern how to deal with nuclear wastes. So based on my past background and existing interest, I am here to learn as much as I can with this present trend ongoing technology. Thank you very much.
Hello, my name is Khalid Rida. I'm from Egypt. I studied 3 years in Egypt, in Egyptian Russian University in Cairo. After that, I come here to Thomas Polytechnic University. To Khalid Rida. And already I finished 5 years, at least the final project for specialists. And the next semester, I will start to design VVR reactor 1300. That's
Hello, my name is Simona Shandalova. I am from Slovakia. I finished my bachelor's degree here at the Faculty of Chemistry at the Division of Radiochemistry, and currently I'm studying at the master's degree that Vladimir spoke about. That is in the field of decommissioning of nuclear facilities. My master's thesis is going to be connected to the reprocessing of uranium metallic fuel. And that is basically what is there to know about me.
My name is Olja Petrovic. I'm coming from Serbia. I work at Vice Institute of Nuclear Science Laboratory for radioisotopes. I have PhD in chemistry. I worked on production of molybdenum technetium generators. I was developing strontium yttrium generators, and where we obtained yttrium, we used to label with different radiopharmaceuticals. With other colleagues in my laboratory, I developed radiopharmaceuticals based on somatostatin, such as DOTA, DOTA-TATE, DOTA-NOC. Many of these radiopharmaceuticals have become drugs in regular clinical use in Serbian hospitals and hospitals around. Currently, I work as a manager of sealed sources. Also, I'm a responsible person for protection in our laboratory and also safety of the hazard from transport in dangerous goods. That's all.
Hi, good afternoon. My name is Zibo Babakan from Uzbekistan. I think I'm alone from Uzbekistan. So I graduated from Tashkent State University in chemistry, and I did my PhD and Doctor of Science dissertation on technology of ceramics, technology of glasses. My last research was technology of fireproof ceramics with graphite and magnesium contains. And now I'm working at the Department of Technology. Technology of silicate materials as teaching professional, and also I am head of international department of Tashkent Chemical Technological Institute. And now I came here to broaden my knowledge about radiochemistry, to develop a little bit my knowledge in this field. Thank you.
Hello, my name is Megha Venugopal. I am from India. I did my bachelor's in India in mechanical engineering, but I was fairly interested in space. So I switched my fields in master's and I switched to experimental nuclear physics and cosmophysics, which was quite the jump. But I had some basic exposure to nuclear physics during my master's. And my thesis was, I just finished my master's a week ago, and my thesis was on cosmophysics. It was not really related to nuclear physics. But the bits I learned in nuclear physics, I wanted to supplement my knowledge, and probably I felt like this course would be a good introduction, and also good for career opportunities as well. So that's why I'm attending this course. And thank you.
Hello, I'm Ayşenur Eravcı. I'm from Turkey. Yeah, it isn't. I'm a nuclear energy engineer and I'm a master's student in nuclear sciences. I'm on my thesis now and I'm working on the adsorption behavior of strontium and cesium with using zeolites. And also I'm synthesizing my own zeolites and magnetic zeolites. That's all. And also I'm a cat mom.
Hello, I am Meryem Seferinoğlu. I came from Turkey. I am radiochemist and I am working at Sinop University as an associated professor. And also I am head of nuclear engineering department. And my research field, radiochemistry and ionization radiology, radiation metrology. Also, I am interested in environmental radioactivity measurement system, especially alpha particle counting system, and uranium, thorium leaching from different sources. By acid leaching or by bioleaching methods. And nowadays, I am also interested with salt composition, which is used molten salt research, molten salt reactor. And that's it. Thank you.
Good evening, everyone. My name is Shulpan Nazarkulova. I'm from Kazakhstan. I'm working at the Kazakh National University. It seems like if in Moscow is MCU, in Kazakhstan is our university, Kazakh National University, in the Department of Inorganic Chemistry and in Laboratory of Radiation Ecology. So in our laboratory, we are working with artificial radionuclides and natural radionuclides. Artificial radionuclides is from nuclear test site, which called semi-Palatin test site. Maybe you hear about this. And with natural radionuclides, because as you know, Kazakhstan is a leader country of producing uranium. So there are a lot of works to investigate radioecological situation in the territories. So we have a lot of projects, and now we are working in the project to investigate influence of application of fertilizers to mobility of radionuclides in the soil. So I'm glad to be here and hope to get some contacts and cooperate in the future. Thank you very much.
I am Süleyman Fatih Özmen, coming from Turkey, University of Akdeniz. I am studying at University of Akdeniz as an associate professor. And I am studying on low-level radioactivity measurements and radioecology mainly, and long and short-term effect of radionuclides on biota in marine ecosystem, we can say in short. And I came here to learn this procedure, what happens to radioactive waste, because nuclear power plant is constructing 300 kilometers to our city by Rosatom, and that's all. I'll see you.